Hello and welcome back. If you're new here, my name is the Sleepy Scientist, and this is a place where curiosity and rest can coexist, where you can learn something genuine while letting the day dissolve away. Tonight, we're turning our attention to something so familiar that we often forget how extraordinary it is: the sun. Maybe you had a long day. Maybe your mind is still turning over conversations, tasks left undone, the small anxieties that follow us into the evening. That's okay. You're here now, and for the next while, all you need to do is listen. Let these words wash over you like gentle waves. If you drift off halfway through, that's not a failure. It's exactly what this is for. Before we begin, if you enjoy falling asleep to science, consider subscribing. It helps this quiet corner of the internet continue to exist, and you'll never miss another journey into the cosmos. There's no pressure, no urgency, just an invitation. Now let's begin. The sun is 4.6 billion years old, roughly middle-aged for a star of its type. Think about that number for a moment. 4.6 billion years. It's been shining steadily for longer than life has existed on Earth. Longer than the continents have had their current shapes. Longer than the mountains have stood. When the sun first ignited, Earth was a molten ball of rock, inhospitable and violent. There were no forests, no oceans with waves, no atmosphere to scatter blue light across a sky. And yet, the sun was already there, burning with the same steady fusion that powers it today. It's been a constant companion through every epoch of Earth's history, through the age of dinosaurs, through the rise of mammals, through the evolution of creatures who would eventually look up and wonder what that bright disk in the sky actually was. The sun witnessed all of it, patient and indifferent, simply doing what stars do, converting hydrogen into helium, releasing light and warmth as a byproduct of existence. What's remarkable is that it's only middle-aged. It has roughly another 5 billion years ahead of it, give or take a few 100 million. In the story of the sun, we exist in a brief, forgettable chapter, a few pages in a very long book. And yet, those pages contain everything we know. Everyone we've loved, every sunset you've ever watched fade into dusk. The sun contains 9.86% of all the mass in our entire solar system. All the planets, moons, asteroids, and comets combined make up barely a rounding error compared to our star. When we think about the solar system, we tend to imagine it as a collection of worlds: Earth, Mars, Jupiter, Saturn with its rings. We picture spacecraft visiting distant moons, asteroids tumbling through the asteroid belt, comets trailing their glowing tails. It feels like a rich, populated neighborhood of space. But in terms of mass, in terms of actual substance, the solar system is really just the sun. Everything else is leftover crumbs, debris from the formation, process, the scraps that didn't fall into the star. Jupiter, the largest planet, seems immense. You could fit over 1/300 Earths inside it. And yet, Jupiter is only about 1,000th the mass of the sun. All the planets together don't even amount to a single percentage point. This puts things in perspective, doesn't it? We live on a tiny rock, orbiting a massive sphere of burning plasma, in a solar system that's really just one object with some decorative dust around it. The sun is the gravitational anchor, the energy source, the central fact around which everything else arranges itself. Without it, there would be no planets, no orbits, no delicate balance that allows for liquid water and life. There would just be cold, dark space, with perhaps a few icy rocks drifting aimlessly through the void. Light from the sun takes 8 minutes and 20 seconds to reach Earth. This means we're always seeing the sun as it was over 8 minutes ago. We live in its gentle past. It's a strange thought, isn't it? When you look up at the sun during the day, though please, don't look directly. Your eyes are precious. You're not seeing it as it is right now. You're seeing it as it was when you were probably doing something else entirely. Making breakfast, perhaps, brushing your teeth, checking your phone. Light is fast, the fastest thing in the universe, in fact. Nothing can travel faster. And yet, even at that incredible speed, it takes over 8 minutes to cross the distance between the sun and Earth. If the sun suddenly vanished, poof, gone, removed from existence by some cosmic magician, we wouldn't know for over 8 minutes. The sky would remain bright, the day would continue, and then without warning, darkness would fall. Of course, the sun isn't going anywhere. It's remarkably stable, remarkably predictable. But this 8-minute delay is a reminder that distance and time are woven together in ways our everyday experience doesn't prepare us for. We live in the sun's past, bathed in light that started its journey before we began the actions we're currently engaged in. It's like receiving letters from someone who wrote them 8 minutes ago, close enough to feel immediate, far enough to be a whisper from another moment in time. The sun is not actually yellow. It emits white light that only appears yellow through Earth's atmosphere. From space, astronauts see it as brilliant white, revealing how much our sky colors our perception. This is one of those facts that feels almost like a betrayal. We've been drawing the sun as a yellow circle since childhood. Yellow crayons, yellow paint, yellow construction paper cut into cheerful rays. Teachers, books, cartoons, they all agree the sun is yellow. But step outside the atmosphere, beyond the blue sky that scatters light and gives our days their color, and the sun reveals its true nature. It's white. A brilliant, searing white that combines all colors of the visible spectrum. The yellow we see is an artifact of Earth's atmosphere, which scatters shorter blue wavelengths more than longer red and yellow ones. The same scattering that makes the sky blue makes the sun appear more yellow than it actually is. It's a gentle reminder that so much of what we perceive is filtered through the medium we exist in. The air we breathe, the atmosphere that protects us, also transforms what we see. Astronauts, floating in the silence of space, see a different sun than we do, one that's perhaps more honest, but also more harsh, more alien. Here on Earth, we get the softened version, the one that's been filtered through miles of air, rendered a bit warmer, a bit more familiar. Perhaps that's fitting. We're creatures adapted to this atmosphere, to this filtered light. The yellow sun isn't wrong. It's just our version of the truth. 1 million Earths could fit inside the sun, with room to spare. Yet the sun is considered a fairly average-sized star, a cosmic middle ground. It's difficult to grasp scales this large, isn't it? 1 million of anything feels abstract. 1 million seconds is about 11.5 days. $1 million would solve most people's immediate financial concerns. 1 million Earths sounds like the setup to a joke or a riddle. But it's true. The sun is so large that you could pack 1 million copies of our planet inside its volume and still have space left over. Not 1 million Earths arranged neatly, mind you. That would leave gaps. But 1 million Earths worth of volume. crushed down and filled into the sun's sphere. Every city, every ocean, every mountain range, every person, animal, and plant, all of it 1,000,000 times over, and it would still fit. And here's the humbling part. The sun is average. It's a middle-of-the-road star, neither particularly large nor particularly small. There are stars out there, red supergiants like Betelgeuse or UY Scuti, that could swallow not just Earth, but the entire inner solar system. Stars so large that the sun itself would be a barely visible dot if placed inside them. And on the other end of the spectrum, there are red dwarfs, tiny stars that burn slowly and dimly for trillions of years, outlasting everything else in the universe. The sun sits comfortably in the middle, which might be why it's hospitable to life. Not too big, not too small, not too hot, not too cool. Just right, in a Goldilocks sort of way, for a planet like Earth to maintain liquid water and evolve complex chemistry. The sun is technically classified as a G-type main sequence star, or G2V on the stellar classification system. This clinical description belies the fact that it's the most important object in our local universe. There's something wonderfully mundane about this classification, isn't there? G2V. It sounds like a parking spot or a vitamin supplement. Not exactly poetic language for the blazing heart of our solar system, the engine of photosynthesis, the reason you can read these words right now. Astronomers classify stars based on their temperature, size, and what's happening in their cores. The G tells us the sun is a yellow-white star with a surface temperature around 5,500 degrees Celsius. The 2 is a subclass, indicating where it falls within the G category. The V means it's a main sequence star, actively fusing hydrogen in its core, in the prime of its life. It's stable, predictable, middle-aged. In the grand catalog of stars, the sun is entry number. Well, it depends on which catalog you're using, but it's one star among hundreds of billions in our galaxy alone. G2V is a common type. There are likely tens of billions of stars similar to the sun in the Milky Way. From a cosmic perspective, there's nothing special about it. It's not the biggest, not the brightest, not the oldest or the youngest. And yet, to us, it's everything. It's the difference between a living world and a frozen rock. It's the energy that powers ecosystems, drives weather, enables civilization. Every calorie of energy you've ever consumed can be traced back, directly or indirectly, to sunlight. Every breath you take depends on plants that convert solar energy into chemical energy. The sun might be G2V in the catalog, but in our story, it's the main character. The sun rotates, but not as a solid body. Its equator spins faster than its poles. The equator completes one rotation in about 25 days, while the poles take 35 days, creating a slow, eternal shear. This is called differential rotation, and it happens because the sun isn't solid. It's made of plasma, superheated gas where electrons have been stripped from atoms, creating a churning, flowing sea of charged particles. Imagine trying to spin a ball of honey or a sphere of thick syrup. Different parts would rotate at different speeds, creating internal friction, swirls, and eddies. That's what's happening on the sun, but on a scale so vast it's hard to comprehend. The equator races ahead, completing its circuit in 25 days, while the polar regions lag behind, taking 35 days to make the same journey around. This differential rotation is partly responsible for the sun's complex magnetic field. As the equator spins faster, it drags magnetic field lines with it, twisting and tangling them like threads being wound around a spool, at different speeds. These tangled magnetic fields eventually break through the surface, creating sunspots, solar flares, and all the dynamic weather we associate with solar activity. It's a reminder that the sun, despite appearing as a simple, unchanging disk in the sky, is actually a turbulent, dynamic object. It's constantly churning, constantly rearranging itself. There's no solid surface to stand on, no fixed reference point, just layers upon layers of plasma, each rotating at its own pace, creating patterns of motion that ripple through the entire star over decades and centuries. Ancient Greeks believed the sun was a god named Helios, who drove a chariot across the sky each day. In a way, they weren't entirely wrong. The sun does govern the daily rhythm of nearly all life on Earth. The Greeks imagined Helios rising from the Eastern Ocean each morning, his golden chariot pulled by fire-breathing horses, crossing the sky in a grand arc, then descending into the Western Ocean at dusk to rest. It's a beautiful story, filled with the kind of anthropomorphic poetry that ancient myths do so well. Of course, we know now that the sun doesn't move across the sky. Earth rotates, giving us the illusion of solar movement. The sun is, relatively speaking, stationary, though it's actually hurtling through space at hundreds of thousands of miles per hour. But that's another fact for another time. The chariot is a metaphor, the god a personification of something the Greeks observed but couldn't fully explain. And yet, the core insight remains true. The sun governs the rhythm of life. It dictates when we wake and when we sleep, when plants photosynthesize and when they rest. It drives the seasons, the weather, the migration patterns of animals. Entire ecosystems are choreographed to the sun's daily and yearly cycles. Farmers plant and harvest by it. Cities organize their schedules around it. Even our biology is tuned to it. Circadian rhythms that follow the 24-hour cycle of day and night. So perhaps Helios was a metaphor for a deeper truth. The sun is not just a physical object, but a force that structures reality. Not a god, exactly, but something so fundamental to existence that it might as well be. The Greeks were trying to explain why the sun mattered, why it couldn't be ignored, why it deserved reverence. In that sense, they understood something essential, even if the chariot itself was fiction. The sun has no solid surface. It's made entirely of superheated plasma. What we see as its surface is actually just the layer where it becomes opaque to our eyes. This is a difficult concept to accept at first. We're used to surfaces. The ground beneath your feet, the walls of your room, the screen you might be looking at right now. All solid, all definite. Even liquids have surfaces. The top of a glass of water, the boundary between ocean and air. But the sun has no such boundary. If you could somehow survive the heat and approach the sun, you wouldn't find a place where you could land. You'd just keep sinking through increasingly dense layers of plasma, getting hotter and hotter, until you were vaporized long before reaching anything resembling a core. The surface we see, the photosphere, is simply the layer where the sun transitions from transparent to opaque. It's where photons can finally escape into space after their long journey from the core. Below that visible layer, the sun continues, denser, hotter, more chaotic. Above it, there are more layers, the chromosphere, the corona, regions of even higher temperature but lower density. It's all sun all the way through, with no clear divisions except the ones we impose based on temperature and density, gradients. This makes the sun fundamentally alien. It's not like anything we experience in our daily lives. It's a ball of plasma held together by gravity, where material is constantly rising, falling, and churning in massive convection currents. There's no place to stand, no stable reference point, just motion, heat, and light all the way down. The temperature at the sun's core reaches 27 million degrees Fahrenheit, 15 million degrees Celsius. At those temperatures, matter exists in states we can barely comprehend, let alone recreate on Earth. 27 million degrees. It's a number so large it loses meaning. The hottest places on Earth, lava flows, blast furnaces, lightning strikes, are a few thousand degrees at most. The hottest we've achieved in laboratories, in fusion reactors and particle accelerators, approaches tens of millions of degrees, but only for fractions of a second in tiny controlled volumes. The sun's core maintains 15 million degrees Celsius continuously throughout its entire central region for billions of years. At these temperatures, atoms don't exist as we normally think of them. Electrons are stripped away, leaving bare nuclei careening through a dense soup of plasma. These nuclei move so fast that when they collide, they overcome the electromagnetic force that would normally repel them, allowing nuclear fusion to occur. This is where the sun's energy comes from. Hydrogen nuclei fusing into helium, releasing energy in the process. It's the same reaction that powers hydrogen bombs, but the sun does it with remarkable control and consistency. 4 hydrogen nuclei combine to form one helium nucleus, and in the process, a tiny amount of mass is converted directly into energy, according to Einstein's famous equation, E mar mc2. That tiny amount of mass, multiplied by the speed of light squared, equals an enormous amount of energy. And this has been happening every second for 4.6 billion years. The core of the sun is an inferno beyond our ability to truly imagine, a place where the fundamental forces of the universe are laid bare, where matter and energy dance together in fusion's ancient rhythm. The sun loses about 4 million tons of mass every second through nuclear fusion. Yet it's so massive that it can sustain this loss for billions more years without noticing. 4 million tons per second. It sounds catastrophic, doesn't it? Like the sun is hemorrhaging mass, bleeding away its substance at an alarming rate. If Earth lost 4 million tons every second, we'd be gone in about a day and a half. The entire planet vanished. But the sun is not Earth. The sun is so massive, about 2 x 1030 kilograms, which is a 2 followed by 30 zeros, that losing 4 million tons per second is like you or me losing a few skin cells. It's not even noticeable. The sun has been doing this for 4.6 billion years, and it's still only halfway through its fuel supply. It can continue at this rate for another 5 billion years without running out. This mass loss isn't waste exactly. It's the price of doing business. When hydrogen fuses into helium in the sun's core, a tiny fraction of the mass, about 0.7%, is converted directly into energy. That energy radiates outward, eventually reaching us as light and heat. The mass doesn't disappear. It transforms into the photons that warm your skin, power photosynthesis, drive weather patterns, make life possible. Einstein showed us that mass and energy are two sides of the same coin, interchangeable under the right conditions. The sun is the universe's demonstration of this principle, converting 4 million tons of itself into pure energy every single second, and doing so with such casual efficiency that it will continue long after our species is forgotten. Galileo was one of the first to observe sunspots through a telescope in 1612, challenging the belief that the sun was perfect and unchanging. These dark blemishes proved that even our star has moods and weather patterns. Before Galileo, the prevailing view, inherited from Aristotle and embraced by the Church, was that celestial objects were perfect, immutable, divine. The heavens were fundamentally different from Earth. Earth had change, decay, imperfection. The heavens were eternal and flawless. Then Galileo pointed his telescope at the sun, using projection methods to protect his eyes, though he may have damaged his vision later in life through solar observation. And there they were, dark spots on the face of the sun, imperfections, blemishes, and more than that, they moved. Over days and weeks, Galileo watched them drift across the sun's surface, proving that the sun rotated. The heavens, it turned out, were not so different from Earth after all. This was revolutionary, even dangerous. Galileo's observations contributed to the mounting evidence that the old cosmology was wrong, that Earth was not the center of the universe, that celestial objects were physical things subject to change and motion. For these and other observations, Galileo would eventually face the Inquisition, forced to recant his support of the heliocentric model. But the sunspots remained. They couldn't be unseen. They're still there today, appearing and disappearing in an 11-year cycle. Dark and cooler regions where magnetic fields inhibit convection. They're reminders that the sun is not a perfect, unchanging sphere of light, but a dynamic, complex object with weather and seasons of its own. Even stars have bad days. The sun produces the equivalent energy of 100 billion hydrogen bombs every single second. Fortunately, we're shielded by 93 million miles of empty space and Earth's magnetic field. 100 billion hydrogen bombs every second. It's the kind of number that should be terrifying, and perhaps it is, in an abstract way. But the terror is softened by distance and by the gentle, diffuse way that energy reaches us. A hydrogen bomb is devastating because all that energy is released in a fraction of a second in a small area. The sun releases far more energy, but it's spread across its entire surface, radiating outward in all directions. By the time it reaches Earth, 93 million miles away, it's diluted to a gentle warmth. The light that falls on your face during a sunny afternoon contains immense power, but it's spread so thin, arriving so gradually, that it's soothing rather than destructive. We're also protected by Earth's magnetic field, which deflects charged particles from the solar wind, and by our atmosphere, which absorbs harmful radiation. Without these shields, the sun's output would sterilize the surface of our planet. Life as we know it couldn't exist. But with these protections in place, the sun becomes not a weapon, but a benefactor, the ultimate source of nearly all energy on Earth. It's a delicate balance, too close to the sun, like Mercury, and the heat is unbearable. Too far, like the outer planets, and you're left in perpetual cold. Earth sits in what astronomers call the habitable zone, the Goldilocks region, where the sun's fusion furnace is powerful enough to warm us, but distant enough not to incinerate us. 100 billion hydrogen bombs per second, transformed by distance into the gentle sunshine of a spring morning. If you could stand on the sun's surface, which you couldn't, you'd weigh about 28 times your Earth weight. Gravity there is so intense that it would crush any known material almost instantly. Imagine weighing 28 times what you weigh now. If you're 150 pounds, you'd suddenly weigh 4,200 pounds, over 2 tons. Your legs wouldn't support you. Your bones would fracture under the load. Your cardiovascular system would struggle to pump blood against that gravity. You'd collapse, and then the heat would vaporize you before you had time to comprehend what was happening. But let's ignore the heat for a moment and just think about the gravity. The sun's mass is so enormous that it creates a gravitational field 28 times stronger than Earth's at its surface. This gravity is what holds the sun together against the outward pressure of fusion in its core. Without gravity, the sun would explode like a bomb. Without fusion, the sun would collapse under its own gravity. The two forces are in perfect balance, a standoff that's lasted billions of years. This intense gravity affects everything on the sun. Material rising from below is pulled back down. Plasma arching in prominence loops is constantly fighting against gravitational pull. Even light, massless though it is affected. Gravitational redshift causes photons to lose a tiny bit of energy as they climb out of the sun's gravitational well. And this is all on the surface, a place that doesn't really exist as a solid boundary. Deeper into the sun, gravity becomes even more intense, squeezing matter to incredible densities in the core. It's this gravitational compression that creates the temperatures and pressures necessary for fusion. Gravity is the architect of stars, the force that builds them and sustains them throughout their lives. The sun makes a sound, but we can't hear it through the vacuum of space. Scientists have converted its pressure waves into sound waves. It hums at frequencies far below human hearing, like the universe's deepest bass note. Sound, as we experience it, is a wave traveling through a medium, air, water, solid materials. It needs something to vibrate. In the vacuum of space, there is no medium and therefore no sound. The sun's roar, if it has one, is silent across the cosmic distance. But the sun does vibrate. Its surface oscillates with millions of different frequencies simultaneously, rising and falling in patterns created by pressure waves bouncing around inside. These oscillations are how scientists study the sun's interior through helioseismology, the solar equivalent of seismology, which studies Earth's interior through earthquake waves. Researchers have taken these oscillations and converted them into sounds we can hear. When you listen to these recordings, the sun sounds like a deep, resonant hum, a drone that's almost felt rather than heard. It's eerie and beautiful, like the sound of a Tibetan singing bowl or the deepest notes of a pipe organ. Some frequencies are so low they're measured in millihertz, oscillations that take minutes to complete a single cycle. This is the sun singing to itself, a private concert performed in the vacuum of space. Each note corresponds to a different mode of vibration, a different way the sun can resonate. By analyzing these patterns, scientists can determine the sun's internal structure, its rotation rate at different depths, and the speed of sound waves moving through its layers. The sun is an instrument, and we've learned to read its music. The sun generates energy through nuclear fusion, fusing hydrogen atoms into helium at its core. This is the same process that powers hydrogen bombs, but the sun does it with perfect, controlled consistency. Fusion is the ultimate energy source, the dream of unlimited, clean power that scientists have been chasing for decades. We've achieved it in bombs, where fusion reactions run wild and uncontrolled, releasing devastating energy in microseconds. We've achieved it in experimental reactors, where we can sustain fusion for seconds or minutes in tiny volumes, consuming more energy than we produce. But the sun has been doing it effortlessly for 4.6 billion years. Every second, roughly 600 million tons of hydrogen is converted into helium in the core. The process requires temperatures of 15 million degrees Celsius and immense pressure, conditions that exist naturally in the sun's core due to gravitational compression. 4 hydrogen nuclei fuse together through a series of steps to form one helium nucleus. In the process, a small amount of mass is lost and converted into energy. This energy is released as gamma rays, high-energy photons that begin their long journey from the core to the surface. It's a journey that can take tens of thousands to hundreds of thousands of years, as the photons are absorbed and re-emitted countless times, gradually losing energy and shifting toward visible wavelengths. By the time they reach the surface and escape into space, they've transformed from gamma rays into the visible light and infrared radiation that warm our planet. The sun makes fusion look easy, but it's anything but. The conditions required are extreme, and sustaining them requires a delicate balance. Too much fusion and the star would expand, cooling the core and slowing the reaction. Too little fusion and gravity would compress the core further, heating it and speeding up the reaction. The sun self-regulates, maintaining equilibrium through feedback loops that have kept it stable for billions of years. A photon of light created in the sun's core can take between 10,000 and 170,000 years to reach the surface. It bounces around randomly in the dense interior, taking a drunkard's walk before finally escaping into space. This is one of the most beautiful and counterintuitive facts about the sun. When a gamma-ray photon is created in the core through fusion, you might expect it to travel straight out at the speed of light, reaching the surface in a matter of seconds. After all, light is fast, and the sun, while large, is only about 432,000 miles in radius. But the interior of the sun is incredibly dense, especially near the core. Photons can't travel more than a tiny fraction of an inch before being absorbed by an atom. That atom then re-emits the photon in a random direction. The new photon travels another tiny distance and gets absorbed again. Over and over, billions upon billions of times, the photon is absorbed and re-emitted, each time in a random direction. This is called a random walk, and it's incredibly inefficient. The photon might move inward for a while, then outward, then sideways. It's like trying to leave a crowded room by taking a random step in any direction every second. You'd bounce around for a very long time before finally finding the exit. For photons in the sun, this process takes tens of thousands to hundreds of thousands of years, depending on the exact path they take. And with each absorption and re-emission, the photon loses a little energy. It starts as a high-energy gamma ray and gradually shifts to X-rays, then ultraviolet, then visible light and infrared. By the time it finally reaches the photosphere and escapes into space, it's been transformed from a deadly gamma ray into the gentle visible light that makes plants grow and warms your skin. The light falling on your face right now began its journey in the sun's core long before human civilization existed. Every second, the sun converts 600 million tons of hydrogen into helium. In that same second, 4 million tons simply vanish, converted entirely into the energy that lights our world. 600 million tons of hydrogen. It's hard to visualize that much mass. The largest supertankers can carry about 500,000 tons of oil. So every second, the sun fuses the equivalent of 1/200 fully loaded supertankers worth of hydrogen. And of that, 4 supertankers worth of mass is converted directly into energy. This is E-mc2 in action, Einstein's famous equation that shows mass and energy are interchangeable. The c in that equation is the speed of light, and when you square it, multiply it by itself, you get an enormous number. That means even a tiny amount of mass converts into a huge amount of energy. In the sun's case, the 4 million tons of mass lost every second becomes 3.8 x 1026 watts of power. That's 380 trillion watts. To put that in perspective, all of human civilization currently uses about 18 trillion watts of power. The sun produces more than 20 billion times that amount every single second. And it's been doing this for billions of years, and will continue for billions more. The fuel supply is so vast, the process so efficient, that the sun barely notices the loss. This is the magic of fusion. It's the most efficient energy source in the universe, short of matter-antimatter annihilation. It's what powers all stars, from the smallest red dwarfs to the largest supergiants. It's the reason stars can shine for millions, billions, even trillions of years. And it's the process we're trying desperately to replicate on Earth, because if we could, we'd have access to nearly limitless clean energy. The sun has been showing us how for 4.6 billion years. We're still learning to follow its example. The sun's energy output is so consistent that it varies by less than 0.1% over time. This remarkable stability has allowed life on Earth to evolve in a relatively predictable climate for billions of years. Imagine if the sun were erratic, brightening and dimming by 10% or 20% over short periods. Earth's climate would swing wildly between ice ages and hothouse conditions. Oceans might freeze solid, then boil away, then freeze again. Life would struggle to adapt to such chaos. Complex ecosystems, which depend on predictable seasons and temperature ranges, probably couldn't exist. But the sun is remarkably steady. Its output varies by less than 0.1% over the course of its 11-year activity cycle. There are small fluctuations. More sunspots mean slightly more energy output. Fewer sunspots mean slightly less. But these variations are tiny compared to the sun's total luminosity. For all practical purposes, the sun is a constant light source. This stability is a consequence of the sun's self-regulating fusion process. When fusion rates increase, the core heats up and expands slightly, which lowers the density and slows the fusion rate back down. When fusion rates decrease, the core cools and contracts, increasing density and speeding fusion back up. It's a natural thermostat, maintaining equilibrium automatically. This consistency has been a gift to life on Earth. It means that over evolutionary timescales, millions and billions of years, the sun's output has been predictable enough for life to adapt gradually. Yes, the sun has been slowly brightening over its lifetime. It's about 30% brighter now than when it first formed. But that change has been gradual enough for Earth's climate systems and life itself to adjust. We owe our existence, in part, to the sun's steady, reliable nature. It's the kind of star you can depend on. Nuclear fusion in the sun requires temperatures so high that atoms move fast enough to overcome their natural repulsion. It's a delicate dance where conditions must be just right. Too cold and fusion stops. Too hot and the star would explode. Atomic nuclei are positively charged, and like charges repel each other. This is basic electromagnetism, a force you experience every time you push two magnets together, North Pole to North Pole. They resist, pushing back against each other. For atomic nuclei, this repulsion is strong. They really don't want to merge. To force them together, they need to be moving incredibly fast. At temperatures of 15 million degrees Celsius, hydrogen nuclei are zipping around at tremendous speeds. When they collide head-on with enough energy, they can overcome the electromagnetic repulsion and get close enough for the strong nuclear force to take over. The strong force is attractive at very short ranges, and once nuclei get close enough, it pulls them together, fusing them into a new, heavier nucleus. But the temperature can't be too high. If the core became significantly hotter, fusion rates would increase dramatically, releasing more energy. This would cause the core to expand and heat the outer layers, potentially leading to instability. The sun could swell up or even blow itself apart in extreme cases. Stars much more massive than the sun burn through their fuel quickly and die young, sometimes exploding as supernovae. The sun sits in a sweet spot, massive enough that its core reaches fusion temperatures, but not so massive that it burns too hot and too fast. It's a Goldilocks star in more ways than one. The balance between gravity, trying to crush the star, and fusion pressure, trying to blow it apart, is what keeps the sun stable. This equilibrium is the reason we have sunlight, seasons, and the time necessary for life to evolve from single cells to civilizations capable of understanding the star that made them possible. The sun has different layers, each with its own temperature and density: core, radiative zone, convective zone, photosphere, chromosphere, and corona. Each layer tells a different story of how energy transforms as it journeys from creation to release. The sun is not uniform. It's not a simple ball of fire, but rather an onion of distinct regions, each with its own character, its own physics, its own role in the grand process of turning mass into light. At the center is the core, where fusion happens. This is the engine room, the furnace, the place where 4 hydrogen nuclei become 1 helium nucleus and release energy. Moving outward from the core, we enter the radiative zone, a thick shell where energy moves primarily through radiation, photons being absorbed and re-emitted, slowly working their way outward over tens of thousands of years. Beyond that is the convective zone, where the plasma becomes less dense, and energy transfer shifts from radiation to convection. Hot plasma rises toward the surface, cools, and sinks back down, creating massive circulation currents. This is where the sun starts to feel more like a boiling pot of water, with material physically moving up and down rather than just photons bouncing around. Then we reach the photosphere, the visible surface, where the sun becomes opaque and photons can finally escape into space. This is what we see when we look at the sun, a bright yellow-white disk with occasional dark sunspots. Above the photosphere is the chromosphere, a thin reddish layer visible during eclipses, and beyond that, the corona, the sun's outer atmosphere, a halo of superheated plasma extending millions of miles into space. Each layer is a chapter in the story of solar energy. Born in the core, energy spends millennia trapped in the radiative zone, gets churned in the convective zone, emerges at the photosphere, and finally escapes through the chromosphere and corona. It's a journey from creation to freedom, and we're the recipients of the light that completes that journey. In the sun's radiative zone, energy moves outward through radiation, like light passing through fog. Photons are absorbed and re-emitted countless times, creating that centuries-long journey to freedom. The radiative zone extends from the core to about 70% of the sun's radius. It's a region of extreme density where matter is packed so tightly that photons can barely move. Picture trying to walk through a dense forest where the trees are only inches apart. You'd constantly be bumping into trunks, forced to change direction, making very slow progress forward. That's what happens to photons in the radiative zone. They're created in the core with high energy, gamma rays, and immediately collide with an atom. The atom absorbs the photon and quickly re-emits it, but in a random direction. The new photon travels a tiny distance and hits another atom. Absorbed, re-emitted, absorbed, re-emitted. Each interaction takes a fraction of a second, but there are so many interactions, trillions upon trillions, that the overall journey takes tens to hundreds of thousands of years. During this journey, the photon gradually loses energy. Each time it's absorbed and re-emitted, there's a chance it'll come out with slightly less energy, shifted toward longer wavelengths. Gamma rays become X-rays. X-rays become ultraviolet. Ultraviolet becomes visible light. By the time a photon reaches the top of the radiative zone, it's much less energetic than when it started. This process is called radiative diffusion, and it's the primary way energy escapes the sun's interior. It's slow, inefficient, and patient. The photons don't mind. They're massless, timeless entities bouncing around in the dark for longer than human civilization has existed, gradually working their way toward the surface, where they'll finally see open space and freedom. The convective zone is where hot plasma rises and cool plasma sinks, like water boiling in an enormous pot. These convection currents are responsible for the sun's magnetic field and its turbulent personality. About 200,000 kilometers below the photosphere, conditions in the sun change. The temperature and pressure drop to a point where radiation becomes less efficient at transporting energy. The plasma can't radiate heat away fast enough, so it starts to do what any fluid does when heated from below. It convects. Hot plasma becomes buoyant and rises toward the surface, carrying energy with it. When it reaches the photosphere, it releases that energy as light and heat, cools down, and sinks back into the interior to be heated again. This creates massive circulation patterns, convection cells that can be thousands of kilometers across. The largest of these cells, called supergranules, are about 30,000 kilometers in diameter and can last for a day or two before breaking up and reforming. This convective motion does more than just transport energy. It also generates the sun's magnetic field. Moving plasma is moving charged particles, and moving charges create magnetic fields. The complex churning motions of the convective zone twist and amplify these fields, creating the sun's large-scale magnetic structure. This is called the solar dynamo, and it's responsible for the 11-year activity cycle, sunspots, solar flares, and all the dynamic phenomena we observe. The convective zone is where the sun develops its weather, its personality, its moods. The lower layers of the sun are relatively calm and orderly, energy flowing smoothly outward through radiation. But in the convective zone, things get chaotic. plasma churns and roils, magnetic fields tangle and snap, and the sun becomes the dynamic, active star we observe. It's the difference between still water and a rolling boil. The visible surface of the sun, called the photosphere, is actually quite thin, only about 300 miles deep. Everything we see is happening in a layer thinner than the distance from New York to Washington, D.C. 300 miles sounds like a reasonable distance. A long drive, perhaps, or a short flight. But in the context of the sun, which has a radius of about 432,000 miles, it's incredibly thin. The photosphere is less than 0.1% of the sun's radius, a delicate shell where the transition from opaque to transparent happens. Below the photosphere, the sun is so dense that photons can't escape. They're constantly absorbed and re-emitted. Above it, the density drops enough that photons can finally travel freely into space. This transition zone is what we perceive as the sun's surface, but it's not a surface in any solid sense. It's just the layer where optical depth reaches a critical value, where the sun stops being opaque and starts being transparent. If you could somehow observe the photosphere up close without being vaporized, you'd see a granular texture. Thousands of bright cells separated by darker boundaries. These are the tops of convection cells, hot plasma rising from below. Each granule is about the size of Texas, and they appear and disappear on timescales of about 8 to 20 minutes. The photosphere is constantly churning, a boiling surface of fire that only looks calm and smooth from 93 million miles away. This thin layer is where the sun's energy finally escapes after its long journey from the core. Photons that spent tens of thousands of years bouncing around in the interior suddenly find themselves free, racing outward at the speed of light. In just over 8 minutes, they'll cross the void and arrive at Earth, where they'll warm your skin, power a solar panel, or be absorbed by a leaf and turned into chemical energy through photosynthesis. Everything begins in this thin, turbulent layer, 300 miles deep. The photosphere has a temperature of about 10,000 degrees Q, 5,500 degrees C, hot enough to vaporize any known material. Yet this is considered relatively cool compared to what lies beneath and above. 10,000 degrees Fahrenheit. It's difficult to find comparisons that make this temperature comprehensible. The melting point of iron is about 2,800 degrees. The surface of Venus, the hottest planet in our solar system, is around 900 degrees. The flame of a blowtorch reaches perhaps 3,000 degrees. The photosphere is hotter than all of these by a factor of 3 or more. At these temperatures, most materials we interact with daily would not just melt or burn. They would vaporize instantly, turning from solid to gas without passing through a liquid phase. Metals, rocks, ceramics, none of them could survive. Even carbon, one of the most heat-resistant elements, sublimes, turns directly from solid to gas at around 6,900 degrees Kelvin in normal atmospheric pressure conditions. The photosphere would destroy it. And yet, as far as the sun is concerned, the photosphere is relatively cool. The core is 15 million degrees Celsius. The radiative zone is several million degrees. Even the base of the convective zone is over 1 million degrees. The photosphere, at a mere 5,500 degrees Celsius, is positively chilly by comparison. This is what happens at the edge of a star. The temperature drops dramatically as you move away from the fusion core. But here's the strange part. If you move further outward from the photosphere, into the chromosphere and corona, the temperature starts rising again. the corona reaches temperatures of over 1,000,000 degrees Celsius, far hotter than the photosphere below it. This seems to violate basic thermodynamics. Heat should flow from hot to cold. So how can the outer atmosphere be hotter than the surface? This is the coronal heating problem, one of the great mysteries of solar physics, and we'll return to it soon. Granules on the sun's surface are actually convection cells, each about the size of Texas. They appear and disappear in about 8 minutes, making the sun's surface look like it's constantly boiling. If you could watch the sun's photosphere in real time with sufficient resolution, you'd see it's not smooth at all. The surface is covered in bright cells, granules, separated by darker lanes. These aren't static features painted on the sun. They're alive, dynamic, constantly forming and dissolving. Each granule represents the top of a convection cell, rising from the convective zone below. Hot plasma reaches the surface, spreads out, releases its energy as light and heat, then cools and sinks back down along the edges of the granule. The bright centers are where hot material is rising. The dark edges are where cooler material is sinking. The temperature difference is only about 300–400 degrees Celsius, but that's enough to create visible contrast. The lifetime of a typical granule is about 8 to 20 minutes. In that brief time, it rises, spreads, cools, and sinks. New granules form continuously as fresh plasma rises from below. The entire photosphere is a constantly shifting mosaic of these cells, a boiling surface that never rests. There are millions of granules covering the sun at any given moment, creating a texture that's only visible through high-resolution telescopes. This granulation pattern is direct evidence of convection, of heat being transported by moving material rather than just radiation. It's similar to what you'd see if you looked at the surface of boiling water or heated oil, though on a vastly different scale. Each granule is roughly 1,000 kilometers across, about the distance from Dallas to Chicago, and they're turning over every few minutes, a constant cycle of rising and falling that helps the sun shed the energy produced in its core. The chromosphere is a reddish layer above the photosphere, visible during solar eclipses. Its name means color sphere in Greek, named for its brief, rosy appearance when the moon blocks the brighter photosphere. Under normal circumstances, the chromosphere is invisible to us. The photosphere below it is so much brighter that it overwhelms the chromosphere's faint light. It's like trying to see a candle flame next to a searchlight. The searchlight drowns out the candle. But during a total solar eclipse, when the moon perfectly blocks the photosphere, the chromosphere becomes visible for a few precious seconds. It appears as a thin reddish ring around the moon's dark disk, a delicate color that stands out against the darkness of the sky and the pearly white corona beyond it. This reddish color comes from hydrogen alpha emission, hydrogen atoms in the chromosphere absorbing and emitting light at a specific red wavelength. The chromosphere is thin, only about 2,000 to 3,000 kilometers deep, and it's an irregular layer with spikes and jets extending upward. These jets, called spicules, shoot material into the corona at speeds of 20 or 30 kilometers per second. There are hundreds of thousands of spicules at any given time, creating a forest of plasma jets around the sun. Each spicule lasts only a few minutes before falling back or being absorbed into the corona. The chromosphere is also where we start to see the temperature inversion that makes the sun's outer atmosphere so puzzling. The temperature at the base of the chromosphere is around 4,500 degrees C, cooler than the photosphere below it. But as you move upward through the chromosphere, the temperature starts to rise, reaching about 20,000 degrees C at its upper boundary, before jumping dramatically to over 1,000,000 degrees in the corona. How and why this happens is still not fully understood. Mysteriously, the sun's corona, its outer atmosphere, is hundreds of times hotter than its surface. This violates our everyday understanding of heat, like bathwater being hotter than the flame heating it. The corona is one of the strangest features of the sun. It extends millions of kilometers into space, a tenuous halo of plasma that's visible during total solar eclipses as a pearly white crown around the moon's silhouette. It's beautiful, ethereal, and completely baffling. The photosphere, the visible surface, is about 5,500 degrees C. The chromosphere above it reaches maybe 20,000 degrees C. But the corona, further from the sun's fusion core, is over 1,000,000 degrees Celsius, sometimes reaching 2 or 3 million degrees in active regions. This doesn't make sense according to basic thermodynamics. Heat flows from hot regions to cold regions. You can't heat something to a higher temperature than your heat source without adding energy from somewhere else. So where is that energy coming from? Scientists have been puzzling over this for decades. The leading theory involves the sun's magnetic field. Magnetic field lines threading through the corona can become twisted and tangled by the sun's rotation and convective motions. When these field lines reconnect, snapping and rearranging themselves, they release enormous amounts of energy, heating the plasma around them. This is called magnetic reconnection, and it might be responsible for the corona's extreme temperatures. Another possibility involves waves, Alfvén waves, that travel along magnetic field lines, carrying energy from the photosphere into the corona, where it's dissipated as heat. Or perhaps it's a combination of both mechanisms. The truth is, we're still not entirely sure. The corona is a reminder that even our closest star, the one we've studied for centuries, still holds mysteries. Even after all this time, the sun can surprise us. Scientists still don't fully understand why the corona is so hot, a puzzle called the coronal heating problem. The leading theories involve magnetic energy and waves, but the complete answer remains elusive. This is one of the beautiful things about science. There are still open questions, still phenomena we don't fully understand. The sun is 93 million miles away, yet we can't explain why its outer atmosphere is so much hotter than its surface. We've sent spacecraft to study it, built sophisticated models, observed it across multiple wavelengths of light, and still the complete picture escapes us. The Parker Solar Probe, launched in 2018, is designed partly to investigate this mystery. It's flying closer to the sun than any previous spacecraft, actually passing through the corona to take measurements from within. Early data has already provided insights, confirming the presence of magnetic reconnection events and Alfvén waves, for instance. But the full explanation is still being pieced together. What we do know is that the corona is not uniformly hot. It has structure, bright active regions above sunspots where temperatures are highest, dark coronal holes where temperatures are lower and fast solar wind streams out into space, and quiet regions in between. The heating mechanisms might vary from place to place. making the coronal heating problem not just one puzzle, but several related ones. It's humbling in a way. We can calculate the fusion rates in the sun's core with remarkable precision. We can predict eclipses thousands of years into the future. We can model the sun's evolution over billions of years, but we still don't fully understand why the corona is hot. Nature always has a few secrets left to reveal, always another layer of mystery beneath what we think we know. The sun's magnetic field flips completely every 11 years. North becomes south, and south becomes north. This quiet revolution happens with such regularity that we can set our clocks by it, yet we still don't fully understand why. Imagine if Earth's magnetic field flipped every 11 years. Compasses would point south instead of north, then flip back again. Migratory animals that use magnetic fields for navigation would need to constantly recalibrate. Aurora would appear in different patterns. It would be strange, disorienting, a fundamental change to our planetary environment. The sun does this regularly, predictably, as part of its 11-year activity cycle. At solar minimum, the sun's magnetic field is relatively organized, with a clear north pole and south pole, much like Earth's. As the cycle progresses towards solar maximum, the magnetic field becomes increasingly tangled and complex due to differential rotation and convective motion. Sunspots appear in greater numbers, representing regions where strong magnetic fields emerge through the surface. At solar maximum, the field is chaotic, with magnetic field lines twisted and knotted across the sun. Then as the cycle winds down toward the next solar minimum, the field reorganizes itself, but with reversed polarity. What was north is now south, and vice versa. Another 11 years later, it flips, again returning to the original configuration. So the full magnetic cycle is actually 22 years, two 11-year cycles with opposite polarity. We know this happens, and we can observe it with magnetometers and by tracking sunspot polarities. But the underlying mechanism, the solar dynamo that generates and reverses the field, is still not completely understood. We have models that reproduce the basic behavior, but the details are complex and still being refined. The sun keeps its rhythm, flipping its poles with clockwork regularity, whether we understand why or not. Sunspots are cooler regions on the sun's surface where intense magnetic fields emerge. They appear dark only by contrast. They're still about 60,500 degrees Kiev, hotter than anything on Earth. When you look at images of the sun's surface, sunspots appear as dark blemishes, sometimes alone, sometimes in groups that span distances larger than Earth itself. The word dark is misleading, though. These regions aren't dark in any absolute sense. They're still radiating enormous amounts of light and heat, far more than any furnace or fire we could create on Earth. Sunspots appear dark because they're cooler than their surroundings. The photosphere around them is about 5,500 degrees Celsius, while sunspots are roughly 3,500 to 4,500 degrees Celsius. That's a significant difference, more than 1,000 degrees, and it's enough to make them appear darker by contrast. But if you could somehow isolate a sunspot and view it against the darkness of space, it would shine brilliantly, glowing white hot. The cooling happens because of magnetic fields. Intense magnetic field lines emerge from below the surface at sunspot locations, breaking through the photosphere like steel cables piercing through fabric. These magnetic fields are so strong, thousands of times stronger than Earth's magnetic field, that they interfere with convection. They act like barriers, preventing hot plasma from rising to the surface as efficiently. With less hot material reaching the surface, that region cools down relative to its surroundings. Sunspots come in pairs or groups with opposite magnetic polarity. One spot where field lines emerge from the surface, another where they loop back down. They're connected beneath the surface by arching magnetic field lines, creating structures that can persist for days or weeks before breaking apart. As the sun rotates, we watch these spots drift across the visible disk, appearing on the eastern edge, traveling across, and disappearing over the western edge. Galileo watched this same motion 4 centuries ago, using it to calculate the sun's rotation period. The sun follows an 11-year activity cycle, alternating between solar maximum, many sunspots, and solar minimum, few sunspots. We're currently living through this cycle, though most of us never notice its rhythm. Right now, as you listen to these words, the sun is somewhere in its cycle, perhaps approaching a maximum with dozens of sunspot groups scattered across its surface, or maybe descending toward a minimum where days pass with no spots at all. The cycle is remarkably regular. Historical records, going back centuries through telescopic observations, and even further through indirect measurements like tree rings and ice cores, show this 11-year pattern persisting with remarkable consistency. There are variations. Some cycles are stronger than others, some last 10 years while others last 12, but the overall pattern holds. At solar minimum, the sun appears calm and featureless. Sunspots are rare or absent. Solar flares are infrequent. The solar wind flows steadily but quietly. The sun's magnetic field is relatively organized and simple. Then gradually, sunspots begin appearing at high latitudes, around 30 to 40 degrees north and south of the equator. As the cycle progresses, more spots appear, and they appear at lower and lower latitudes, drifting toward the equator. At solar maximum, the sun is active and chaotic. Dozens of sunspot groups might be visible at once. Solar flares erupt regularly. Coronal mass ejections hurl billions of tons of plasma into space. The sun's magnetic field is tangled and complex. Then, as the cycle wanes, activity decreases. Sunspots become less frequent, appearing closer to the equator before disappearing altogether. The sun returns to minimum, the magnetic field flips, and the whole process begins again with reversed polarity. Most people never notice this cycle because the sun's total brightness barely changes, less than 0.1%. But those who study the sun, those who monitor space weather, those who rely on radio communications that can be disrupted by solar storms, they track the cycle carefully, knowing that solar maximum brings increased risk of technological disruption and increased opportunity for spectacular auroras. The largest sunspot ever recorded was 15 times wider than Earth. These dark storms on the solar surface can be larger than the space between Earth and the Moon. In April 1947, astronomers observed a sunspot group so large it was visible to the naked eye. When properly filtered, of course, never looked directly at the sun. The main spot in this group had an area of about 6,000 millionths of the solar disk, which translates to roughly 15 Earth diameters across. 15 Earths. Try to visualize that. If you lined up 15 Earths side by side, they would stretch about 120,000 miles, roughly half the distance from Earth to the Moon. And this was a single cool region on the sun's surface, a place where magnetic fields were so intense they suppressed convection across an area larger than Jupiter. Sunspots this large are rare. Most are much smaller, perhaps 1 or 2 Earth diameters across. But occasionally, perhaps once or twice a decade, during active periods, truly enormous spot groups appear. These monster spots are often the source of major solar flares and coronal mass ejections because the magnetic energy stored in such large, complex regions can be enormous. When a sunspot this large faces Earth, there's increased risk of space weather impacts. The magnetic field lines threading through and around the spot can become unstable and reconnect explosively, releasing energy equivalent to billions of nuclear bombs. If directed toward Earth, the resulting radiation and particles can disrupt satellites, interfere with radio communications, induce currents in power grids, and create stunning auroras visible far from the poles. The sun reminds us occasionally that despite being 93 million miles away, it's still capable of affecting our technological civilization in profound ways. Solar flares are massive explosions on the sun that release as much energy as millions of nuclear bombs. They happen in seconds, sending radiation across the solar system at the speed of light. Imagine all the energy humanity has ever produced. Every fire ever lit, every engine ever run, every power plant ever built, compressed into a few seconds and released from a region smaller than Earth. That's a solar flare. These explosions occur when magnetic field lines in the sun's atmosphere become twisted and tangled, storing enormous amounts of magnetic energy. Eventually, the stress becomes too great, and the field lines snap and reconnect in a new configuration, like a rubber band that's been twisted until it suddenly releases. The energy stored in the magnetic field is converted almost instantly into heat, particle acceleration, and radiation. The radiation from a flare spans the electromagnetic spectrum: radio waves, visible light, ultraviolet, X-rays, and gamma rays. The most intense radiation reaches Earth in about 8 minutes, traveling at the speed of light. When a powerful flare occurs on the Earth-facing side of the sun, we detect it almost immediately as a sudden brightening in X-ray and extreme ultraviolet wavelengths. This radiation can ionize Earth's upper atmosphere, disrupting radio communications, especially high-frequency signals used for aviation and maritime communication. Flares are classified by their X-ray brightness: B class, smallest; C class, M class; and X class, largest. Within each class, there's a logarithmic scale from 1 to 10. An X-class flare is 10 times more powerful than an M-class flare. The largest flare ever recorded was in November 2003, so powerful it overloaded the sensors measuring it. Scientists estimate it was about X45, 45 times more powerful than an X1 flare. The sun, when provoked, can be spectacularly violent. A coronal mass ejection, CME, can hurl 1 billion tons of solar material into space at speeds of millions of miles per hour. When they hit Earth's magnetic field, they create the auroras, nature's light shows powered by solar storms. While solar flares are bursts of radiation, coronal mass ejections are actual clouds of plasma, charged particles with embedded magnetic fields, ejected from the sun's corona into interplanetary space. Think of a flare as a flash of light from an explosion, while a CME is the shrapnel. A single CME can contain 1 billion tons of material, though some of the largest contain much more. This plasma is ejected at speeds ranging from a few hundred to several thousand kilometers per second. That's millions of miles per hour. The fastest CMEs can reach Earth in as little as 15 to 18 hours, though most take 2 to 3 days to cross the 93 million miles between Sun and Earth. When a CME arrives at Earth, it doesn't hit the atmosphere directly. We're protected by Earth's magnetic field, which deflects most of the solar wind and CME particles around the planet. But the CME's magnetic field can interact with Earth's field, causing it to compress and distort. On the night side of Earth, magnetic field lines can snap and reconnect, accelerating particles down into the upper atmosphere near the poles. These particles, mostly electrons and protons, collide with oxygen and nitrogen atoms in the atmosphere, exciting them and causing them to emit light. Oxygen emits green and red light. Nitrogen emits blue and purple. The result is the aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. These dancing curtains of light, shimmering and shifting across the polar skies, are the visible signature of the sun's weather reaching Earth. They're beautiful, mesmerizing, and a reminder that we live inside our star's atmosphere, protected but not isolated from its storms. The Carrington event of 1859 was the most powerful solar storm in recorded history. It caused auroras visible near the equator and made telegraph systems spark and catch fire. If it happened today, it could cripple our electrical infrastructure. On the morning of September 1st, 1859, British astronomer Richard Carrington was observing sunspots when he witnessed something extraordinary. Bright flashes appearing on the sun's surface. He was seeing a massive solar flare, one of the first ever observed, though he didn't know what it was at the time. About 17 hours later, the associated coronal mass ejection reached Earth, an unusually fast arrival indicating the CME was traveling at extreme speed. The impact on Earth's magnetic field was dramatic. Auroras were visible as far south as the Caribbean and Hawaii. People in the Rocky Mountains woke up in the middle of the night thinking it was dawn because the sky was so bright with auroral light. Newspapers reported that you could read by the aurora's glow, but the most dramatic effects were on the telegraph system, the only electrical technology widely deployed at the time. Telegraph operators reported receiving electric shocks from their equipment. Papers caught fire. Some telegraph lines continued to work even after their power supplies were disconnected, powered solely by the electrical currents induced in the wires by the changing magnetic field. If a Carrington-level event happened today, the consequences would be far more severe. Our modern civilization depends on electrical grids, satellites, GPS, radio communications, and countless other technologies vulnerable to intense geomagnetic storms. A direct hit from a Carrington-class CME could damage transformers across power grids, potentially causing blackouts lasting weeks or months. Satellites could be damaged or destroyed. GPS and radio communications could be disrupted. The economic impact could be in the trillions of dollars. It's not a matter of if such an event will happen again, but when and whether we'll be prepared. Solar prominences are enormous loops of plasma that arch above the sun's surface, guided by magnetic fields. Some can span distances greater than the diameter of Jupiter, hanging in the sun's atmosphere for weeks. Prominences are among the most beautiful and dramatic features visible on the sun. They appear as bright arcs or loops extending from the solar surface, sometimes reaching heights of 100,000 kilometers or more, 10 times the diameter of Earth. These structures are made of relatively cool, dense plasma, around 10,000 Degsica compared to the million-degree corona around them. They appear bright when viewed at the edge of the sun, at the limb, because they're denser than their surroundings. When viewed against the bright disk of the sun, the same structures appear as dark filaments because the cooler plasma absorbs more light than it emits compared to the hotter photosphere behind it. Prominences are supported and shaped by magnetic field lines that emerge from the photosphere, loop through the corona, and return to the surface. Plasma flows along these field lines, trapped by the magnetic structure. Some prominences are relatively stable, persisting for days or weeks, with plasma slowly flowing along the loops. Others are more dynamic, with material shooting upward or raining back down along curved paths. Occasionally, a prominence becomes unstable and erupts, releasing the plasma into space. These erupting prominences often become coronal mass ejections, hurling billions of tons of material outward. Watching time-lapse footage of a prominence eruption is mesmerizing. Vast quantities of plasma, following invisible magnetic field lines, lifting off from the sun and expanding into space. It's a reminder that the sun's atmosphere is structured not by pressure and density alone, but by magnetic fields that can support, confine, and accelerate plasma in ways that seem to defy gravity itself. The sun experiences tornadoes of plasma that can be 5 times larger than Earth, spinning at 186,000 amtard. These solar tornadoes last for hours, swirling through conditions that would instantly vaporize our entire planet. In 2011, NASA's Solar Dynamics Observatory captured footage of a massive tornado-like structure on the sun. The rotating column of plasma was about 50,000 kilometers tall, 5 times Earth's diameter, and 20,000 kilometers wide. Material was spinning at speeds up to 300,000 kilometers per hour, fast enough to complete a rotation every few hours. These structures aren't tornadoes in the meteorological sense. They're not driven by temperature differences and pressure gradients in an atmosphere. Instead, they're magnetic phenomena. Twisted magnetic field lines threading through the solar atmosphere create spiral patterns, and plasma, being electrically charged, follows those field lines. The result looks like a tornado, but is actually a different beast entirely. A magnetic flux rope, a bundle of helically twisted field lines with plasma spiraling around them. Solar tornadoes can last for hours, sometimes exceeding a day. They rotate, they rise, they transport mass and energy from lower layers to higher layers. Some eventually become unstable and erupt, contributing to coronal mass ejections. Others gradually dissipate as the magnetic structure unwinds or reconnects with surrounding fields. The conditions within a solar tornado are extreme beyond comprehension. Temperatures of hundreds of thousands to millions of degrees. Magnetic field strengths thousands of times stronger than Earth's field. Plasma densities and pressures that would crush any material we know. And through all of this, the tornado persists. A spiral column of fire spinning at a significant fraction of the speed of light, casually demonstrating physics we can barely replicate in laboratory conditions for microseconds. Spicules are jets of plasma that shoot up from the sun's surface every few seconds, reaching thousands of miles high. The surface of the sun is like a field of grass made of fire, constantly sprouting and dying. If you could observe the chromosphere and transition region between the photosphere and corona with high spatial and temporal resolution, you'd see the surface isn't still. It's covered with thousands of thin jets, spicules, shooting upward at high speed, reaching heights of 3,000 to 10,000 kilometers before either falling back or being absorbed into the corona. These jets are thin, typically only a few hundred kilometers in diameter, but they're ubiquitous. At any given moment, there are hundreds of thousands of spicules on the sun. They appear, shoot upward at speeds of 20 to 30 kilometers per second, reach their maximum height in about 5 to 10 minutes, and then either fade away or fall back to the surface. New spicules form continuously, creating a constantly regenerating forest of plasma jets. Scientists believe spicules play a role in transporting mass and energy from the photosphere and chromosphere into the corona. Each individual spicule carries a relatively small amount of material, but with hundreds of thousands occurring simultaneously and constantly regenerating, the cumulative effect might be significant. Some researchers think spicules might contribute to coronal heating, though this is still debated. There are actually two types of spicules. Type 1, which are the classic spicules that last 5 to 10 minutes, and Type 2, which are faster, shorter-lived, and might be more directly related to heating the corona. Watching time-lapse footage of spicules is like watching grass waving in a breeze, except the grass is made of plasma tens of thousands of degrees hot, and the wind is driven by magnetic fields and pressure waves. The sun's surface is never still, never smooth, never quiet. It's alive with motion at every scale we can observe. The sun emits a constant stream of charged particles called the solar wind. This invisible breeze fills the entire solar system, creating a bubble called the heliosphere that protects us from interstellar radiation. The solar wind isn't wind in the meteorological sense. There's no air rushing past. Instead, it's a stream of charged particles, mostly electrons and protons, flowing outward from the sun's corona at speeds of 300 to 800 kilometers per second. The corona is so hot, millions of degrees, that its particles have enough energy to escape the sun's gravity. They stream outward in all directions, carrying the sun's magnetic field with them. This creates the heliosphere, a vast bubble of solar influence extending far beyond the planets. The heliosphere is shaped somewhat like a comet, with a rounded front facing the sun's direction of motion through the galaxy, and a long tail streaming behind. The solar wind is variable. During quiet periods, it flows steadily from coronal holes, regions where the sun's magnetic field opens out into space. During active periods, coronal mass ejections add bursts of higher density, faster-moving material. The wind also varies with latitude. It's faster near the poles and slower near the equator. When the solar wind reaches Earth, most of it is deflected around the planet by our magnetic field. But some particles are funneled down toward the poles, where they create auroras. The solar wind also interacts with other planets and objects in the solar system. It gives comets their tails. The dust tail points away from the sun due to light pressure, while the ion tail points away due to the solar wind's push. Mars, lacking a strong magnetic field, has been gradually stripped of its atmosphere by the solar wind over billions of years. We're bathed in this particle stream constantly, protected by our planet's magnetic shield, mostly unaware of the invisible breeze blowing past us from the sun. The solar wind travels at about 1 million miles per hour near Earth. You're being pelted by solar particles right now, though Earth's magnetic field deflects most of them around us. 1,000,000 miles per hour. It's hard to grasp that speed. The fastest human-made objects, spacecraft like the Parker Solar Probe or Voyager, travel at perhaps 100,000 to 400,000 miles per hour at their peak velocities. The solar wind moves faster than that, and it does so constantly, streaming outward from the sun in every direction, filling the solar system with a supersonic flow of charged particles. These particles, mostly protons and electrons, with a small fraction of heavier ions, carry energy and momentum. When they encounter obstacles like planets or spacecraft, they interact. Earth is fortunate to have a strong magnetic field generated by its liquid iron core. This field extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere. When the solar wind hits the magnetosphere, it's deflected around Earth, much like water flowing around a boulder in a stream. The boundary where the solar wind first encounters Earth's magnetic field is called the bow shock, analogous to the shock wave that forms in front of a supersonic aircraft. Behind that is the magnetopause, the actual boundary of the magnetosphere. Most solar wind particles are diverted around this boundary and continue past Earth without ever reaching the atmosphere. But some particles, particularly during geomagnetic storms when the solar wind is especially intense, can penetrate the magnetosphere near the poles where the magnetic field lines converge. These particles spiral down into the atmosphere, creating the auroras. So while you're safe from direct bombardment, protected by your planet's magnetic shield, you are, in a sense, constantly surrounded by the sun's exhalation, the 1,000,000-mile-per-hour breeze that our world deflects but cannot entirely escape. The edge of the sun's influence, called the heliopause, extends about 11 billion miles from the sun. Only 5 human-made objects have ever crossed this boundary: the Voyager probes and Pioneers 10 and 11, 11 billion miles. If you traveled at 60 miles per hour continuously, it would take you over 20,000 years to reach that distance. The Voyager spacecraft, launched in 1977 and traveling at about 35,000 miles per hour, took more than 35 years to reach it. The heliopause is where the solar wind finally stops, where it runs into the interstellar medium, the thin gas and dust between the stars. The solar wind is supersonic, meaning it's traveling faster than sound waves can propagate through it. But as it moves outward and spreads over an increasingly large volume, its density and pressure decrease. Eventually, at the heliopause, the pressure from the interstellar medium is strong enough to stop the outward flow of the solar wind. The transition isn't sharp. There's a region called the heliosheath, where the solar wind slows from supersonic to subsonic speeds, compressing and heating. Beyond that is the heliopause itself, and beyond that is true interstellar space, the realm between stars, where the sun's influence fades, and other stellar winds, cosmic rays, and the general galactic environment dominate. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. Pioneers 10 and 11 launched earlier but traveling in different directions and at slower speeds, likely crossed sometime around 2012 and 2027 respectively, though they stopped transmitting data decades ago, so we can't confirm the exact moment. These 5 ambassadors from Earth have left the sun's protective bubble, and are now sailing through the space between stars, carrying golden records with sounds and images from our world. Messages in bottles cast into an ocean far vaster than any our ancestors could have imagined. Solar eclipses are cosmic coincidences. The moon is exactly the right size and distance to perfectly cover the sun's disk. This won't always be true. The moon is slowly drifting away, and in millions of years, total solar eclipses will be impossible. It's one of the most remarkable coincidences in our solar system. The sun is about 400 times larger than the moon, and it's also about 400 times farther away. This means that from Earth's perspective, they appear almost exactly the same size in the sky. When the moon passes directly between Earth and the sun, it can block the sun's bright disk completely, creating a total solar eclipse. The fit is so precise that during totality, the moon's dark disk is surrounded by the sun's corona, the faint outer atmosphere that's normally invisible against the bright photosphere. For a few minutes, daylight turns to twilight. Stars become visible, and the corona shimmers around the black circle of the moon. But this perfect arrangement is temporary on cosmic timescales. The moon is gradually moving away from Earth at about 3.8 centimeters per year, roughly the rate your fingernails grow. This happens because of tidal interactions between Earth and Moon. Earth's rotation is gradually slowing, and angular momentum is being transferred to the Moon, causing its orbit to expand. Millions of years from now, the Moon will be far enough away that it will no longer appear large enough to completely cover the Sun. Total solar eclipses will become impossible. Annular eclipses, where the Moon passes in front of the Sun but appears slightly smaller, leaving a ring of sunlight visible, will still occur, but the spectacular view of the corona during totality will be lost. We're living in an era when our planet's geometry creates one of nature's most beautiful phenomena, and that era is finite. It's a reminder to appreciate the transient alignments and coincidences that make our experience of the universe what it is. During a total solar eclipse, the sun's corona becomes visible, revealing delicate, pearly white structures. For ancient peoples, seeing the sun's crown during an eclipse must have seemed like glimpsing the face of a god. Imagine experiencing a total solar eclipse without understanding what was happening. You're going about your day under normal sunlight, and gradually you notice the light becoming strange, dimmer but also flatter, shadows becoming sharper. The temperature drops, birds stop singing and return to roost. Animals become confused. Then the sun, the constant, reliable source of light and warmth that has governed your entire life, disappears. The sky darkens to twilight. Where the sun should be, there's a black hole surrounded by a shimmering white crown of light. Delicate streamers extending outward, sometimes with reddish prominences visible at the edges. For a few minutes, the world is transformed. Then, just as suddenly, a brilliant point of light appears, the diamond ring effect, and normal daylight floods back. No wonder ancient cultures interpreted eclipses as omens, signs from the gods, cosmic battles between celestial forces. The Babylonians learned to predict them through careful record-keeping, but prediction isn't the same as understanding. Even when you know an eclipse is coming, even when you understand the mechanics of orbital geometry, the experience of totality is profound. That's why eclipse chasers travel the world to stand in the moon's shadow for those few minutes of totality. The corona visible during eclipses is the same corona that's always there, extending millions of miles into space, hotter than the surface below it. But it's so faint, about 1,000,000 times dimmer than the photosphere, that it's invisible when the bright disk is present. Only when the moon blocks that overwhelming light can we see the corona's delicate structure. Streamers following magnetic field lines, bright regions above active areas, darker coronal holes where fast solar wind escapes. For ancient peoples, it was a glimpse of the divine. For us, it's a window into the sun's outer atmosphere, brief and precious. The diamond ring effect during an eclipse happens when the last bit of sunlight shines through a lunar valley. For a few seconds, the sun becomes a ring of light with a brilliant diamond. A moment of accidental perfection. In the final seconds before totality, as the moon's edge covers the last sliver of the sun's photosphere, the sun's light shines through valleys and between mountains on the lunar limb. The moon's edge isn't smooth. It's rugged with craters and mountain ranges, and these irregularities create the diamond ring effect. The corona forms a faint ring around the moon, and one brilliant point of light, the diamond, shines through a lunar valley, creating a ring with a brilliant jewel. It lasts only seconds, sometimes just a fraction of a second, before totality begins or ends. Photographers prize this moment, trying to capture that brief instant when geometry and lighting combine to create something extraordinary. The same effect happens at the end of totality, when the first glimpse of the photosphere reappears. That first point of light is so bright after the darkness of totality that it seems almost unbearably brilliant. A diamond of pure sunlight against the fading corona. Some people prefer the diamond ring at the beginning, in anticipation of totality to come. Others prefer it at the end, a finale to the experience. It's a reminder that beauty often emerges from the precise alignment of circumstances. The moon's orbit, its irregular surface, our position in space and time. If the moon were perfectly smooth, there would be no diamond ring, just a gradual dimming and brightening. The imperfections, the valleys and mountains, create this moment of accidental artistry. The universe, it seems, has an aesthetic sense, or at least we're built to find beauty in the patterns and alignments that emerge from physical law. The sun is traveling through space at about 450,000 miles per hour, carrying the entire solar system along with it. We're on a cosmic road trip around the Milky Way galaxy, though we won't complete one lap for another 225 million years. When you think of the sun, you probably imagine it as stationary with the planets orbiting around it. And that's true from the sun's perspective. The planets do orbit the sun, but the sun itself is not sitting still. It's moving through space at tremendous speed, orbiting the center of the Milky Way galaxy. The galaxy is a rotating disk of stars, gas, and dark matter. The sun sits about 26,000 light-years from the galactic center, in a relatively quiet region between major spiral arms. It's orbiting the galaxy at roughly 450,000 miles per hour, about 200 kilometers per second. At this speed, the sun takes about 225 to 250 million years to complete one orbit. Astronomers call this time period a galactic year or cosmic year. This means that since the sun formed 4.6 billion years ago, it has completed about 20 orbits around the galaxy. When dinosaurs walked the Earth 200 million years ago, the sun was on the opposite side of the galaxy. When the first multicellular life evolved, the sun had completed only about 15 galactic orbits. Human civilization, all of recorded history, has existed for only about 0.2% of a galactic year. We're barely a blip in the sun's cosmic journey, and we're passengers on this journey. Earth, along with all the other planets, is being carried along as the sun orbits the galaxy. The solar system is like a spinning top moving through space. The planets orbit the sun while the sun itself follows its path around the galactic center. From a galactic perspective, the planets trace out spiral or helical paths through space, never actually returning to the same point. The sun has never been exactly where it is now, and it never will be again. We're all travelers on a one-way trip through space and time. The sun is about 26,000 light years from the center of the Milky Way galaxy. We're in the suburbs of our galaxy, in a quiet region called the Orion Spur. The center of the Milky Way, where a supermassive black hole resides, is far away, so far that light takes 26,000 years to make the journey. This is fortunate in a way. The galactic center is a crowded, energetic place. Stars are packed more densely there. Radiation levels are higher. Supernovae and other violent events are more common. It's the downtown of the galaxy, bright and bustling and potentially dangerous. The sun, by contrast, is in the suburbs, a relatively sparse region between the major spiral arms. We're in a small partial arm called the Orion Spur, or Orion Arm, named after the Orion constellation visible from Earth. It's quieter here. Stars are more spread out. The radiation environment is gentler. Some scientists think this location might be one reason why life was able to develop on Earth. Too close to the galactic center, and we'd be exposed to more radiation and gravitational disturbances. Too far out in the galactic hinterlands, and there might not be enough heavy elements for rocky planets and life to form. The sun's galactic neighborhood isn't fixed, though. As it orbits, it moves in and out of spiral arms, experiencing different environments. Spiral arms are regions of higher density where stars form more frequently. They're not physical structures that stars orbit. They're more like traffic jams, density waves moving through the galactic disk. When the sun passes through a spiral arm, the local star density increases, and there might be more nearby supernovae, potentially affecting Earth's climate and evolution through increased cosmic ray exposure. But for now, for this moment in cosmic time, we're in a relatively safe, quiet neighborhood. The view from our galactic suburb includes the Milky Way's band stretching across our night sky, the combined light of billions of stars in the galactic disk seen edge on. We're looking at our own galaxy from inside it, from our comfortable position 26,000 light years from the chaos at the center. There are between 100 and 400 billion stars in our galaxy alone, and the sun is just one of them. Yet to us, it's the most significant star in the universe, the difference between life and lifelessness. 100 billion stars at minimum, possibly 4 times that. The uncertainty comes from the difficulty of counting stars. Many are faint, many are obscured by dust, and the outer edges of the galaxy are hard to observe. But even taking the lower estimate, the sun is one of 100,000 stars in the Milky Way. And the Milky Way is just one galaxy among hundreds of billions in the observable universe. The total number of stars in the observable universe is estimated at around 1023 or 1024. That's 100,000 trillion stars, possibly more. The sun is one star in this incomprehensible multitude. From a cosmic perspective, the sun is unremarkable. It's not especially large or small, bright or dim, hot or cool. It's a middle-aged main sequence G-type star, one of the most common types. There are likely tens of billions of sun-like stars in our galaxy alone. If you could randomly sample stars from the Milky Way, you'd find many that are similar to our sun in mass, temperature, composition, and age. And yet, to us, the sun is everything. It's the source of light that allows us to see. It's the energy source that powers photosynthesis, creating the base of nearly every food chain on Earth. It's the heat source that maintains liquid water on our planet's surface. It's the gravitational anchor that holds our world in a stable orbit. It's the reason our planet has a magnetic field, because its heat drives convection in Earth's core. Every aspect of our existence traces back to the sun in some way. So the sun is both cosmically ordinary and locally extraordinary, a paradox that defines our relationship with it. It's one star among countless trillions, and simultaneously the star that makes everything possible. About 10% of stars in our galaxy are similar to the sun in size and temperature. This means there could be tens of billions of sun-like stars, each potentially surrounded by their own family of worlds. 10% of 100 to 400 billion is 10 to 40 billion sun-like stars in the Milky Way alone. Each one could have planets. Some of those planets might orbit at the right distance to have liquid water. Some might develop life. Some of that life might become complex, intelligent, technological. This is the basis of the Drake equation and the Fermi paradox. If there are billions of sun-like stars with potentially habitable planets, where is everyone? Why haven't we detected signals from alien civilizations? There are many possible answers. Perhaps life is rare, intelligence is rarer still, technological civilizations tend to destroy themselves, or the distances between stars are simply too vast for communication or travel to be practical. But the numbers are provocative. We've discovered thousands of exoplanets orbiting other stars, and many of them orbit sun-like stars at distances where liquid water could exist. Some are probably rocky worlds like Earth. Statistical estimates suggest there could be billions of potentially habitable planets in our galaxy. We're learning that planets are common, solar systems are common, and the conditions for life might be common as well. The sun, then, might be one of billions of stars with habitable worlds. Earth might be one of countless planets where life evolved. We might be one of many intelligent species in the galaxy, separated by distances so vast that communication takes thousands or millions of years. Or we might be alone, the only spark of consciousness in the galaxy, which would make us and our sun unimaginably precious. Either answer, that we're common or that we're unique, is profound, and we don't yet know which is true. But every sun-like star we discover reminds us that our sun, while ordinary in its properties, might be extraordinary in what it has accomplished, nurturing a world where matter became alive and aware. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away. Even traveling at the speed of light, it would take over 4 years to visit our nearest neighbor. 4.24 light-years is about 25 trillion miles. If you could drive there at highway speeds, 60 miles per hour, it would take you 47 million years. If you flew on a commercial airliner at 500 miles per hour, it would take about 6 million years. The fastest spacecraft humans have ever built, the Parker Solar Probe at its peak velocity, would take over 6,000 years to reach Proxima Centauri. This is the fundamental challenge of interstellar travel. Even our nearest stellar neighbor is so far away that reaching it within a human lifetime would require technologies far beyond what we currently possess. We'd need to travel at a significant fraction of light speed, perhaps 10% or 20% of light speed, which would require either enormous amounts of energy or revolutionary propulsion methods we haven't invented yet. Proxima Centauri is a red dwarf, much smaller and dimmer than the Sun, only about 12% of the Sun's mass. It has at least 2 planets, including one called Proxima Centauri b that orbits in the star's habitable zone. This planet might have liquid water, though whether it's actually habitable is uncertain. Red dwarfs like Proxima are prone to intense flares that could strip away a planet's atmosphere. Still, it's tantalizing to imagine. Our nearest stellar neighbor might have a habitable world. If we could somehow reach it, we'd find a system very different from ours. A dim red star that would appear 3 times larger than the Sun appears from Earth, casting a reddish light across any landscapes below. Days and years would be different. The sky would be different. But it would be another solar system, another star with planets, another corner of the galaxy. And it's our next-door neighbor in cosmic terms, even though it's 25 trillion miles away. The universe is vast beyond comprehension. Some stars are over 1,000 times larger than the Sun, so large that they could swallow the orbit of Jupiter. Compared to these red supergiants, our Sun is a mere spark, yet it's exactly the right size for life to flourish nearby. Stars like UY Scuti, Betelgeuse, or VY Canis Majoris are truly enormous. If you replace the Sun with one of these red supergiants, the star's surface would extend past the orbit of Mars, possibly reaching Jupiter's orbit or beyond. Earth would be vaporized deep inside the star's outer layers, long before reaching anything resembling a core. These massive stars live fast and die young. They burn through their fuel at prodigious rates, fusing hydrogen into helium, then helium into carbon, carbon into oxygen, and so on, up the periodic table until their cores are filled with iron. At that point, fusion can no longer generate energy. Fusing iron consumes energy rather than releasing it. The core collapses in a fraction of a second, and the star explodes as a supernova, briefly outshining entire galaxies. The Sun will never do this. It's not massive enough. Its life is longer, steadier, more predictable. It will spend about 10 billion years on the main sequence, fusing hydrogen. It will swell into a red giant, yes, but a modest one compared to the true supergiants. It will gently shed its outer layers as a planetary nebula and become a white dwarf. No explosion, no supernova, no catastrophic end. Just a slow, graceful decline over billions of years. And this moderation, this unremarkable middling nature, might be exactly what allowed life to develop. Stars much larger than the Sun don't live long enough. They burn out in millions of years rather than billions. Not enough time for planets to cool, for atmospheres to form, for chemistry to evolve into biology. The Sun's mediocrity is, in a sense, a gift. It's neither too large nor too small, neither too hot nor too cold, neither too brief nor too eternal. It's just right for the slow, patient process of evolution. The smallest stars, red dwarfs, can be as little as 8% of the Sun's mass. These dim stars will outlive the Sun by trillions of years. They'll be the last lights in the universe. Red dwarfs are the most common type of star in the galaxy, making up perhaps 70% or more of all stars. They're small, as little as 0.08 solar masses, just barely massive enough for fusion to occur. They're dim, emitting mostly in the red and infrared. Proxima Centauri, our nearest stellar neighbor, is a red dwarf. Because they're so small and cool, red dwarfs burn their fuel incredibly slowly. A star like the Sun will exhaust its core hydrogen in about 10 billion years. A red dwarf will take trillions of years, far longer than the current age of the universe, which is only 13.8 billion years. This means that every red dwarf that has ever formed is still on the main sequence, still fusing hydrogen. None have died yet. The universe hasn't been around long enough. These stars will outlast everything. Billions of years from now, when the Sun has become a white dwarf, cooling slowly in the darkness, red dwarfs will still be shining. Trillions of years from now, when the last massive stars have long since exploded or collapsed into black holes, when the universe has expanded and cooled, when galaxies have been torn apart by dark energy, red dwarfs will still be burning steadily, the last islands of light in an increasingly dark cosmos. Eventually, even they will exhaust their fuel. But that won't happen for such an incomprehensibly long time that it's difficult to even conceptualize. By the time the last red dwarf dies, the universe will be almost unrecognizably different from what it is now. Protons might have decayed, black holes might have evaporated through Hawking radiation. The universe might be approaching heat death, maximum entropy, a state of unchanging equilibrium. And then finally, the last red dwarf will flicker out, and the age of starlight will end forever. The Sun outputs more energy in 1 second than all of humanity has used in our entire existence. We harvest less than 1/billionth of the Sun's total energy output, yet it's more than enough to power our entire civilization. Think about all the energy humanity has ever consumed. Every fire ever lit, from the first controlled flames, hundreds of thousands of years, ago to today's wildfires. Every lamp, every light bulb, every street light, every factory, every power plant, coal, oil, gas, nuclear, hydroelectric, wind, solar, every car, truck, train, ship, airplane, every computer, every data center, every heating system in winter, every air conditioner in summer. Add it all together across all of human history, and the Sun produces more than that in a single second. Its power output is 3.8 x 1026 watts. That's 380 trillion watts. By comparison, global human energy consumption is about 18 trillion watts, or 5.7 x 1020 joules per year. The Sun produces that much energy in less than 2 seconds, and we capture only a tiny fraction of what the Sun sends our way. Earth intercepts about 1/billionth of the Sun's total output, the portion that happens to be traveling in our direction. Of that, much is reflected back to space by clouds and ice. Much is absorbed by the atmosphere and oceans. Only a small fraction is captured by plants through photosynthesis, and an even smaller fraction is captured by human technology, like solar panels. Yet even this tiny fraction is enough. The sunlight falling on Earth provides more energy than we could ever use. All the energy in fossil fuels, coal, oil, gas, is ancient sunlight, stored by plants and algae millions of years ago. All renewable energy except geothermal and tidal is ultimately solar energy. Wind is driven by uneven heating. Hydroelectric depends on the water cycle powered by evaporation. And solar panels directly convert sunlight to electricity. The Sun, distant and indifferent, provides abundance. We've barely begun to learn how to accept the gift. Only about 2.45 billionths of the sun's energy actually reaches Earth. We live on a tiny fraction of a fraction, like catching a few drops from an enormous waterfall. The sun radiates energy in all directions equally, creating an expanding sphere of light. Earth is a small target at 93 million miles away. The fraction of the sun's total output that happens to hit Earth can be calculated from geometry, the ratio of Earth's cross-sectional area to the area of a sphere at Earth's orbital distance. That ratio is about 4.5 x 1010, 0.45 billionths. It's an almost incomprehensibly small fraction, and yet it's still an enormous amount of energy in absolute terms. The solar energy reaching Earth is about 174,000 terawatts. That's 174 followed by 15 zeros watts. Compare that to human energy consumption of about 18 terawatts, and you see that the sun delivers about 10,000 times more energy to Earth than we currently use. Most of this energy is absorbed by Earth's surface and atmosphere, driving weather systems, ocean currents, and the water cycle. A tiny fraction, less than 1%, is captured by plants and algae through photosynthesis, converting light energy into chemical energy stored in sugars and other organic molecules. This becomes the base of the food chain, the foundation of all complex life on Earth. We're living on the scraps, the tiny fraction of the sun's output that happens to intersect our planet as it orbits. We're catching a few drops from a waterfall, a few photons from an ocean of light. But those few drops are enough to power a living world, to create weather and seasons, to enable the existence of everything we know and love. The sun's generosity is so vast that even its smallest fraction is overwhelming abundance. If the sun were the size of a beach ball, Earth would be a peppercorn 26 feet away. This tiny scale model reveals just how much of our solar system is empty space. Scale models of the solar system are difficult to create accurately because the distances involved are so much larger than the sizes of the objects. If you make the planets large enough to see, the distances become unmanageably huge. If you make the distances manageable, the planets become invisibly small. But let's try. If the sun is a beach ball, say 2 feet in diameter, then Earth is a peppercorn about 0.09 inches across, sitting 26 feet away. Mercury would be a pinhead 10 feet from the beach ball. Venus would be slightly larger than Earth, about 19 feet away. Mars would be another peppercorn at 39 feet. Jupiter, the largest planet, would be an orange about 135 feet away, nearly half a football field. Saturn would be a smaller orange about 250 feet away. Uranus and Neptune would be grapes at 500 and 780 feet, respectively, nearly 3 football fields away from the beach ball sun. And Pluto? Pluto would be a grain of sand about 1,000 feet away, a fifth of a mile. The Voyager spacecraft, having traveled for over 45 years, would be about 4 miles away from the beach ball in this scale model. The nearest star, Proxima Centauri, would be another beach ball about 7,000 miles away, roughly the distance from New York to Mumbai. This model reveals the fundamental nature of the solar system. It's mostly empty space. The sun and planets are tiny islands in a vast ocean of nothing. The distances between objects are so large compared to their sizes that collisions are rare and encounters are unusual. We orbit through emptiness, held in place by gravity across vast distances, connected but separate, each world its own isolated realm in the darkness. The sun is made of about 73% hydrogen, 25% helium, and 2% heavier elements. This composition is a fossil record of the early universe, when there was almost nothing but hydrogen and helium. In the first moments after the Big Bang, the universe was too hot for atoms to exist. It was a soup of fundamental particles, quarks, electrons, photons, expanding and cooling rapidly. Within the first few minutes, as temperatures dropped to around 1 billion degrees, protons and neutrons could form, and they could stick together to form atomic nuclei. This process, called Big Bang nucleosynthesis, created mostly hydrogen, just single protons, and helium, 2 protons and 2 neutrons, with trace amounts of lithium and beryllium. The proportions were about 75% hydrogen and 25% helium by mass, with everything else being rounding errors. Then the universe cooled further, and nucleosynthesis stopped. For hundreds of thousands of years, the universe was a hot plasma of hydrogen and helium nuclei mixed with electrons and photons. Eventually, around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming neutral atoms. The universe became transparent to light. The cosmic microwave background radiation we detect today is the relic of that moment, and the composition was still roughly 75% hydrogen, 25% helium, almost nothing else. The Sun formed 9 billion years later from a cloud of gas that had been enriched slightly by previous generations of stars. Stars that had fused lighter elements into heavier ones, and then expelled or exploded, scattering those heavier elements into space. So the Sun has about 2% heavier elements: carbon, nitrogen, oxygen, iron, and all the rest, thanks to stars that lived and died before the Sun was born. But the bulk of its composition, the hydrogen and helium, is primordial, unchanged from the early universe. The Sun is made of ancient material carrying within it the chemical signature of cosmic genesis. Every atom heavier than helium in your body was forged inside a star. We are literally made of stardust, though not from our Sun. It came from ancient stars that died before our solar system was born. Carbon, the backbone of organic chemistry and life. Oxygen, which you're breathing right now. Nitrogen, in your DNA. Calcium, in your bones. Iron, in your blood. Phosphorus, in every cell. All of these elements were created by nuclear fusion inside stars. Light elements like carbon and oxygen are made in the cores of ordinary stars like the Sun through helium fusion. Heavier elements up to iron are made in more massive stars through successive stages of fusion. Carbon burning, neon burning, oxygen burning, silicon burning. Elements heavier than iron, gold, silver, uranium, are created primarily in supernova explosions and neutron star collisions, where the extreme temperatures and neutron densities allow for rapid neutron capture. These elements weren't always here. In the early universe, there was only hydrogen and helium. The first generation of stars, population 3 stars, formed from this pristine gas. They lived, fused hydrogen into heavier elements, and died, some exploding as supernovae. The debris from these explosions mixed with the remaining hydrogen and helium, creating slightly enriched gas clouds. Second-generation stars formed from this enriched material, creating even more heavy elements. This cycle repeated over billions of years, gradually increasing the abundance of heavy elements in the galaxy. By the time the solar nebula collapsed to form the Sun and planets 4.6 billion years ago, it contained about 2% heavy elements, enough to build rocky planets like Earth and complex chemistry like life. Every atom in your body heavier than helium was forged in the core of a star that lived and died before the sun existed. You are the universe made conscious, assembled from the ashes of ancient suns. The sun will fuse only about 10% of its hydrogen before it runs out of fuel. Most of its hydrogen will never participate in the fusion process, sitting idle while the core burns away. This seems wasteful, doesn't it? The sun contains enough hydrogen to, in principle, power fusion for 100 billion years or more, if all of it could be fused. But only about 10% of that hydrogen will ever undergo fusion. The rest will remain as ordinary hydrogen throughout the sun's life and beyond. The reason is that fusion only occurs in the core, where temperatures and pressures are high enough. As you move outward from the center, temperature and pressure drop rapidly. Beyond about 25% of the sun's radius, conditions aren't sufficient for fusion. The hydrogen there is too cool, too low pressure. It will never reach fusion conditions. Moreover, even within the core, the sun doesn't perfectly mix. Helium produced by fusion is heavier than hydrogen, so it tends to sink toward the center. Over time, helium accumulates in the core while hydrogen remains in the outer layers. Eventually, the core will be almost entirely helium, while plenty of hydrogen remains in the outer regions of the sun, unused. When the sun exhausts the hydrogen in its core, about 5 billion years from now, fusion will stop there, but there will still be hydrogen in the layers above the core. A shell of hydrogen around the inert helium core will continue fusing, causing the sun to expand into a red giant. But the hydrogen further out, beyond that shell, will never fuse. It will simply be part of the expanding envelope, eventually shed into space as a planetary nebula. Most of the sun's mass will never experience fusion. It's just along for the ride, structural material holding the fusion core in place. By mass, the sun is about 330,000 times heavier than Earth, yet all that mass would still fit inside the orbit of Mercury, making it remarkably dense by cosmic standards. 330,000 Earths. It's difficult to visualize that much mass. Earth has a mass of about 6 x 1024 kilograms. The sun has a mass of about 2 x 1030 kilograms. If you could put them on opposite ends of a cosmic balance scale, you'd need 330,000 Earths to balance one sun. Despite this enormous mass, the sun is relatively compact. Its radius is about 696,000 kilometers, less than 1/4 of Mercury's orbital distance. If the sun were more diffuse, it could easily extend beyond Mercury's orbit. Some red supergiants have radii larger than the orbit of Jupiter. But the sun is relatively dense, held together by its own gravity into a tight sphere. The average density of the sun is about 1.4 grams per cubic centimeter, 1.4 times the density of water. This means the sun would float if you could somehow find an ocean large enough to put it in. Of course, this average hides enormous variation. The core is about 150 times denser than water, denser than lead. The photosphere is less dense than the air you're breathing. The corona is even more tenuous, nearly a perfect vacuum by Earth standards. This density profile is a natural consequence of gravity. The weight of all the outer layers presses down on the core, compressing it to high densities. Without this compression, there wouldn't be enough pressure and temperature for fusion to occur. The sun's mass creates its own furnace through gravitational compression. And that mass, enormous as it is still small by stellar standards. The sun is a middleweight star, neither impressively massive nor remarkably small, just another ordinary star doing what stars do. The Sun's density is about 1.4 times that of water, meaning it would float if there were an ocean large enough. This average hides the extremes. The core is 150 times denser than water, while the outer layers are thinner than air. Imagine an ocean vast enough to hold the Sun, an ocean with a surface area comparable to the size of the solar system itself. If you could place the Sun in this impossible ocean, it would float, bobbing gently with about 40% of its volume submerged and 60% above the waterline. This thought experiment reveals something interesting about the Sun's overall composition. Despite the extreme density of the core, and despite the Sun being a ball of plasma where atoms are partially or fully ionized, its average density is only slightly more than water. This is because so much of the Sun's volume is occupied by the outer layers, the radiative zone, convective zone, and atmosphere, which are much less dense than the core. The core might be 150 times denser than water, but it occupies only a tiny fraction of the Sun's total volume, perhaps 2% or less. The vast bulk of the Sun is material at lower densities. The photosphere has a density comparable to Earth's atmosphere at high altitude. The chromosphere and corona are so tenuous, they're essentially a vacuum by terrestrial standards, with particle densities far lower than anything we'd call a gas on Earth. This density gradient is what allows the Sun to support itself against gravity without collapsing and without exploding. The core is dense enough for fusion to occur, creating outward pressure. The outer layers are tenuous enough that this pressure can support them. If the Sun were uniformly dense throughout, all of it as dense as the core, it would be much smaller and much more massive than it actually is. If it were uniformly as dense as the outer layers, gravity would crush it until the core reached fusion conditions. The Sun has found its equilibrium, a balance between density and temperature, pressure and gravity, across its entire radius. The Sun formed from a collapsing cloud of gas and dust called a solar nebula. Everything in our solar system, planets, moons, asteroids, even us, condensed from the leftover scraps of that ancient cloud. About 4.6 billion years ago, somewhere in a spiral arm of the Milky Way galaxy, there was a cloud of gas and dust floating in space. It was cold, dark, and enormous, perhaps a few light years across, containing enough material to make hundreds or thousands of stars. It had been slowly accumulating for millions of years, enriched by the debris of previous stellar generations. Then something disturbed it. Perhaps a nearby supernova sent a shockwave through the region. Perhaps the density wave of a spiral arm compressed the cloud as it passed through. Whatever the trigger, a small region within the cloud began to collapse under its own gravity. As it collapsed, it began to spin faster. Conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in. The center of this collapsing region became denser and hotter as gravitational potential energy converted to thermal energy. The surrounding material flattened into a disk as it fell inward, like water spiraling down a drain. Most of the mass fell into the center, creating what would become the Sun. The disk around it, perhaps only 1% or 2% of the total mass, would eventually form the planets, moons, asteroids, and comets. This process left its fingerprints throughout the solar system. All the planets orbit in roughly the same plane, the plane of the original disk. Most rotate in the same direction the disk was spinning. The compositional gradient, rocky planets close to the sun, gas giants farther out, reflects the temperature gradient in the disk, with volatile materials like water and methane condensing only in the cooler outer regions. We are, all of us, products of that ancient collapse. The atoms in your body were once part of that cold, dark cloud, slowly falling toward a newborn star. The formation of the sun took about 50 million years from cloud collapse to full ignition. In cosmic terms, this is remarkably quick, like watching ice melt in fast forward. 50 million years sounds like a long time. It's longer than the age of the dinosaurs, longer than complex life has existed on land. But in cosmic terms, it's a blink. Galaxies take billions of years to evolve. Stars live for millions to trillions of years. Even planets take hundreds of millions of years to cool and settle after formation. 50 million years is quick. The collapse started slowly. Gravity is a weak force compared to electromagnetism or the nuclear forces, so it took time for the cloud to overcome its internal pressure and turbulence. Gradually, over perhaps 1 million years, the cloud contracted, getting denser and hotter. As it contracted, the rate of collapse increased. More mass means stronger gravity means faster infall. Within a few million years, the central region had become dense and hot enough to be opaque. Light couldn't escape easily. This proto-sun, still contracting and heating but not yet fusing hydrogen, shone brightly from gravitational energy alone. It was in what astronomers call the T Tauri phase, named after the prototype star of this class. T Tauri stars are young, variable, and energetic, with powerful stellar winds and frequent flares. Around the proto-sun, the disk of remaining material was also evolving. Dust grains were sticking together, forming pebbles, then rocks, then planetesimals, the building blocks of planets. This process was happening simultaneously with the sun's formation. By the time the sun's core finally reached the critical temperature and density for hydrogen fusion to ignite, about 50 million years after the initial collapse, the planets were already beginning to form in the disk around it. The solar system was being born as an integrated system, star and planets together, from the collapse of a single cloud. Before it began fusing hydrogen, the young sun was a protostar, a hot, bright object powered by gravitational contraction. It shone for millions of years before the nuclear furnace finally sparked to life. During this protostar phase, the sun was actually more luminous than it is today. Energy was being released as gravitational potential energy converted to heat, the Kelvin-Helmholtz mechanism. As material fell inward, it accelerated, and when it hit the growing proto-sun, its kinetic energy was converted to thermal energy, heating the star. The protostar was large, perhaps several times the sun's current radius, and relatively cool at the surface, but bright because of its large surface area. As it contracted, it became smaller and denser. The core temperature and pressure increased. This process continued for millions of years, the proto-sun gradually shrinking and heating as gravity squeezed it tighter. Eventually, the core reached about 10 million degrees Celsius. At this temperature, hydrogen nuclei were moving fast enough to occasionally overcome their electromagnetic repulsion and fuse together. At first, these fusion reactions were rare, contributing only a small amount of energy. But as the core continued to contract and heat, fusion rates increased exponentially. There's a threshold, around 15 million degrees, where hydrogen fusion becomes vigorous enough to generate as much energy as gravitational contraction. When that threshold was crossed, the Sun reached equilibrium. The outward pressure from fusion balanced the inward pull of gravity. Contraction stopped. The Sun had arrived on the main sequence, the stable phase where it would spend most of its life. The nuclear furnace had ignited, and it would burn steadily for billions of years. The protostar phase was over. The Sun, properly speaking, had been born. When fusion first ignited, the Sun entered what astronomers call the T Tauri phase, becoming incredibly active and variable. Any planets forming during this phase would have been blasted by intense stellar winds and flares. T Tauri stars are the teenage years of stellar development, energetic, unpredictable, and occasionally violent. The young Sun, newly arrived on the main sequence, was still settling down. Its luminosity varied by 30% or more over time scales of days to years. It produced powerful stellar winds, much stronger than the modern solar wind, that blew away much of the remaining gas in the inner solar system. Massive solar flares were common, far more powerful and frequent than anything the Sun produces today. If Earth had already formed its atmosphere during this phase, much of it might have been stripped away by these early storms. Mars, smaller and with weaker gravity, probably lost much of its early atmosphere this way. The T Tauri Sun was a hostile environment for young planets, but this violence had a purpose. The powerful stellar wind helped clear the solar system of leftover gas and dust, preventing it from falling onto the newly formed planets. It created a relatively clean environment where rocky planets like Earth could cool and solidify. The intense radiation might have driven chemical reactions in the early atmospheres of planets, potentially contributing to the formation of complex organic molecules. This phase lasted perhaps a few million to 10 million years. Gradually, as the Sun settled into stable main sequence fusion, it calmed down. The variability decreased. The stellar wind weakened to its current level. Flares became less frequent and less powerful. By the time the Sun was 100 million years old, it had become the relatively stable star we know today. The planets, meanwhile, had survived the turbulent childhood of their star and were continuing their own evolution toward the worlds we see today. The Sun has been steadily getting brighter throughout its life, about 30% brighter now than when it first formed. Early Earth received less sunlight, yet somehow life emerged, one of the many mysteries of our origins. This brightening happens because as the Sun fuses hydrogen into helium in its core, the mean molecular weight of the core material increases. Helium atoms are heavier than hydrogen atoms, so a helium-rich core is denser than a hydrogen-rich core at the same temperature and pressure. To maintain the same pressure to support the Sun against gravity, the core must contract slightly and heat up. Higher temperature means faster fusion rates, which means more energy output. So the Sun has been gradually getting brighter throughout its main sequence lifetime. When it first ignited fusion 4.6 billion years ago, it was only about 70% as bright as it is today. This creates a puzzle called the faint young sun paradox. If the Sun was significantly dimmer 4 billion years ago, Earth should have been frozen solid. The average temperature should have been below the freezing point of water. Yet geological evidence clearly shows that liquid water existed on Earth's surface at least 3.8 billion years ago, possibly earlier. Somehow, despite receiving less sunlight, early Earth was warm enough for liquid water. The most likely explanation involves greenhouse gases. Earth's early atmosphere probably contained much more carbon dioxide and perhaps methane than today, creating a strong greenhouse effect that trapped heat and kept the surface warm despite the fainter sun. As the sun brightened over billions of years, these greenhouse gases were gradually removed from the atmosphere through chemical weathering and biological processes, maintaining a relatively stable temperature. It's a delicate balance. Too much greenhouse warming and Earth becomes Venus. Too little and it becomes Mars. Somehow, Earth stayed in the habitable range as the sun brightened by 30%. Life not only emerged, but thrived through this long, slow change. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin fusing helium. This will cause it to swell into a red giant, expanding to perhaps 250 times its current size. 5 billion years is a long time, longer than Earth has existed, longer than the sun has already burned, but it's not infinite. The hydrogen fuel in the sun's core is finite, and the clock is ticking. In about 5 billion years, the core will be almost entirely helium, with no hydrogen left to fuse. When that happens, fusion in the core will stop. The core will no longer generate the outward pressure needed to support the sun against gravity. Gravity will begin to win, and the core will start to contract. But as it contracts, it will heat up, gravitational energy converting to thermal energy again, like during the protostar phase. This heating will cause a shell of hydrogen surrounding the core to reach fusion temperatures. This shell of hydrogen burning around an inert helium core will produce more energy than the core fusion did during the main sequence phase. The extra energy will cause the sun's outer layers to expand dramatically. The sun will swell up, becoming larger and cooler at the surface, but much more luminous overall. This is the red giant phase. At its maximum size, the sun might extend to 250 times its current radius, potentially reaching Earth's orbit or beyond. Mercury will definitely be engulfed. Venus will probably be engulfed. Earth's fate is uncertain. It depends on exactly how large the sun becomes and how much mass the sun loses during the expansion. Even if Earth's orbit expands enough to avoid being swallowed, the surface will be heated to thousands of degrees. The oceans will boil away. The atmosphere will be stripped. Earth will become a scorched, airless rock orbiting a dying star. During its red giant phase, the sun will likely engulf Mercury and Venus, and possibly Earth. Our planet will either be consumed or left as a scorched, airless rock orbiting a dying star. Imagine standing on Earth 5 billion years from now. If there were still a surface to stand on, if you could somehow survive. Looking up, you wouldn't see a distant sun appearing as a small, bright disk. You'd see an enormous, dim red globe filling much of the sky, extending perhaps 30 degrees across, 60 times larger in appearance than today's sun. It would be dim enough to look at directly, glowing a dull red, its surface visibly granulated with massive convection cells. The heat would be unbearable. Even if Earth's orbit expanded due to the sun's mass loss, as the sun sheds its outer layers, its gravitational grip weakens, and planets drift outward, it wouldn't be enough. The sun as a red giant will be hundreds of times more luminous than today. Earth's surface temperature would rise to thousands of degrees. Any water would have boiled away long before. The atmosphere would have been stripped by the intense solar wind. The surface would glow red hot, possibly molten. If Earth does get engulfed, if the sun's surface extends to Earth's orbit or beyond, our planet would be inside the sun's outer atmosphere. The corona and chromosphere would envelop Earth. The drag from the tenuous plasma would cause Earth's orbit to decay. It would spiral inward, deeper into the sun's envelope, until it eventually vaporized or fell into the denser layers below. Earth would be consumed, its atoms added to the sun's outer layers, eventually shed into space as part of a planetary nebula. This is the fate awaiting our planet in 5 billion years. Life on Earth has a finite deadline, imposed by the evolution of our star. Long before then, perhaps in only 1 billion years, Earth will become uninhabitable as the sun's gradual brightening pushes us out of the habitable zone. But the final end comes when the sun leaves the main sequence and swells into a giant. Our world, if it still exists, will die with our star. After the red giant phase, the sun will shed its outer layers in a beautiful display called a planetary nebula. These glowing shells of gas are some of the most beautiful objects in the universe's way of making art from death. During the red giant phase, the sun will lose mass steadily through a powerful stellar wind. The outer layers, loosely bound by gravity, will be gradually blown away into space. This process will accelerate as the sun evolves, eventually becoming unstable with pulsations that eject material in shells. The result is a planetary nebula, a shell or multiple shells of glowing gas expanding outward from the dying star. The name is misleading. Planetary nebulae have nothing to do with planets. Early telescopic observers thought they looked like planetary disks, hence the name, but they're actually stellar remnants. The gas is ionized by ultraviolet radiation from the hot central star, what remains of the sun's core, causing it to glow with characteristic colors. Oxygen emits green and blue-green light. Hydrogen emits red. Nitrogen and sulfur add other hues. Planetary nebulae come in many shapes: spherical shells, elongated ellipses, bipolar structures with 2 lobes, rings, spirals, and more complex forms. The shapes depend on factors like rotation, magnetic fields, and whether the star had a binary companion. The sun's planetary nebula will probably be relatively simple, perhaps a spherical or slightly elliptical shell, since the sun doesn't have a companion star to create more complex structures. These nebulae are beautiful and brief. They last only tens of thousands of years before the gas disperses into the interstellar medium, enriching the galaxy with the heavy elements created during the star's life. Planetary nebulae are one way the universe recycles material. The sun will return most of its mass to space, where it might eventually form new stars and planets. From death comes new birth. The sun's final act will be to beautify the galaxy for a cosmic moment before fading away. The sun will eventually become a white dwarf, a dense, Earth-sized ember slowly cooling over trillions of years. This stellar remnant will contain about half the sun's current mass, compressed into a sphere the size of our planet. After shedding its outer layers as a planetary nebula, what remains is the sun's core, mostly carbon and oxygen produced during helium fusion, surrounded by a thin layer of helium and hydrogen. This core, no longer supported by fusion, is held up against gravity by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. The result is a white dwarf, an incredibly dense object about the size of Earth. Half the Sun's mass, 100,000 times Earth's mass, compressed into Earth's volume. A teaspoon of white dwarf material would weigh several tons. The surface gravity would be about 350,000 times Earth's gravity. If you could stand on a white dwarf, you couldn't. You'd be crushed instantly. You'd weigh millions of pounds. The white dwarf will be initially very hot, around 100,000 degrees Celsius at its surface, glowing brilliant blue-white. But with no fusion to generate energy, it will simply radiate away its stored heat into space, slowly cooling over billions of years. First, it will glow white, then yellow, then red, then eventually dim to invisibility. A black dwarf, though that name is theoretical since the universe isn't old enough yet for any white dwarf to have cooled completely. This cooling process takes an incredibly long time. The white dwarf has enormous heat capacity, and it's a good insulator. It will take trillions of years, far longer than the current age of the universe, for the Sun's white dwarf remnant to cool to near absolute zero. By then, the universe will be vastly different than today. Stars will have long since stopped forming. Galaxies will have been torn apart by cosmic expansion. The Sun's white dwarf will be one of countless cold embers drifting through a dark, expanding cosmos. A teaspoon of white dwarf material would weigh about 15 tons. On Earth, matter can be compressed so tightly that atoms are crushed together, creating some of the densest material possible. 15 tons, the weight of several cars, compressed into a volume you could hold in your hand. This density is possible because of the strange quantum mechanical nature of matter at extreme densities. In ordinary matter, atoms are mostly empty space. The nucleus is tiny, and electrons orbit in clouds far from the nucleus. Atoms don't touch. They're kept apart by electromagnetic forces. But in a white dwarf, the pressure is so extreme that atoms are crushed. The electrons are stripped away, and the matter becomes a degenerate electron gas. The electrons are packed so tightly that quantum mechanics prevents them from being compressed further. This electron degeneracy pressure is what supports the white dwarf against gravity. Not thermal pressure from heat, but quantum pressure from the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state. The density of a typical white dwarf is about 1 million times the density of water, or about 1 ton per cubic centimeter. A sugar cube of white dwarf material would weigh a ton. A teaspoon would weigh 15 tons. A basketball would weigh millions of tons. And this is still not the densest matter can be. Neutron stars are even denser, and black holes condense matter to infinite density at their singularities. If you could somehow bring a teaspoon of white dwarf material to Earth, it would be catastrophic. The immense gravity of this tiny sample would be impossible to contain. It would sink through whatever you placed it on, through the ground, possibly all the way to Earth's core. Of course, without the pressure of the rest of the white dwarf, the material would probably explode as the electrons recombined with nuclei, releasing enormous energy. White dwarf matter exists in that state only because of the extreme conditions in a white dwarf. It's a form of matter that can't exist anywhere else in the universe. The white dwarf sun will eventually cool to become a black dwarf, a cold, dark cinder floating in space. However, the universe isn't old enough yet for any black dwarfs to exist. They're still theoretical objects. The universe is currently 13.8 billion years old. White dwarfs cool extremely slowly. It takes roughly 10 billion years for a white dwarf to cool from 100,000 degrees to about 5,000 degrees. To cool all the way to near absolute zero and become a black dwarf would take trillions of years, perhaps 1015 to 1020 years, depending on the mass and composition. The universe simply hasn't been around long enough. Every white dwarf that has ever formed, from the death of every star massive enough to become a white dwarf, but not massive enough to explode as a supernova, is still glowing. Even the oldest white dwarfs, formed perhaps 10 or 11 billion years ago, are still radiating heat. They're faint, certainly. Some glow only, in infrared, too cool to emit visible light, but they're not yet truly cold. Black dwarfs are theoretical objects that will exist only in the far future, when the universe is vastly older than it is today. By the time the first black dwarfs form, the universe will have changed dramatically. Star formation will have ceased. All the gas will have either formed stars or been dispersed too thinly to collapse. Galaxies will have merged or been torn apart by cosmic expansion. The cosmic microwave background will have cooled to nearly absolute zero. In this dark, cold future, black dwarfs will be among the few remaining objects. They'll be invisible, detectable only by their gravity or by the extremely faint radiation they might emit from residual heat or from exotic processes like proton decay, if that occurs. The sun's black dwarf remnant, if you could find it in the immensity of space, would be a cold sphere the size of Earth, composed of crystallized carbon and oxygen, darker than the space around it, a tombstone marking where a star once lived. The sun will not explode as a supernova. It's not massive enough. Only stars at least 8 to 10 times more massive than the sun end their lives in these spectacular explosions. Supernovae are among the most energetic events in the universe, briefly outshining entire galaxies. They occur when massive stars, those with at least 8 to 10 solar masses, exhaust all possible fusion fuels in their cores. These stars fuse hydrogen into helium, helium into carbon and oxygen, then carbon into neon and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. Iron is the end of the line. Fusing iron consumes energy rather than releasing it, so when the core becomes primarily iron, fusion stops. Without fusion to generate outward pressure, the core collapses catastrophically. In less than a second, it shrinks from about the size of Earth to a sphere only 20 kilometers across. The collapse is so violent that it rebounds, sending a shock wave outward through the star. The shock wave blows apart the outer layers in a supernova explosion, releasing in a few seconds more energy than the sun will produce in its entire 10 billion year lifetime. The sun will never experience this. It's not massive enough to fuse elements beyond carbon and oxygen. Its core will never become iron. Instead of collapsing and exploding, the sun will gently puff off its outer layers as a planetary nebula and settle into retirement as a white dwarf. No spectacular explosion. No seeding of the galaxy with freshly forged heavy elements. Just a quiet fade into darkness. In a way, this is fortunate. If the sun were massive enough to go supernova, it would have burned through its fuel in only a few million to a few 100 million years. Not enough time for life to evolve on Earth. Supernovae are spectacular, but they're also brief and violent. The sun's gentler fate is the price of its longevity, and that longevity is what gave life time. to emerge and evolve. The Sun is currently about halfway through its main sequence lifetime, the stable phase where it fuses hydrogen. We're living during the Sun's prime years, before old age brings dramatic changes. The Sun has been on the main sequence for about 4.6 billion years. It has perhaps another 5 to 6 billion years before it exhausts the hydrogen in its core and begins its evolution into a red giant. This means we're living right around the midpoint of the Sun's stable, hydrogen-fusing lifetime. In human terms, if the Sun's main sequence lifetime were compressed into 100 years, we'd be living when the Sun is about 46 to 50 years old, middle-aged, still vigorous, but no longer young. The Sun has already changed noticeably from its youth. It's about 30% brighter than when it first arrived on the main sequence. It will continue to brighten gradually over the next few billion years. For life on Earth, this midpoint is significant. The early Sun was too faint for complex life to easily develop on Earth's surface without a strong greenhouse effect. The future Sun will be too bright, eventually making Earth uninhabitable, even with reduced greenhouse gases. There's a window in the Sun's lifetime when Earth is comfortably habitable, and we're living in that window. Some astrobiologists think we might actually be living toward the end of Earth's habitability window. In perhaps 500 million to 1 billion years, the Sun's increasing luminosity might make Earth too hot for complex life, even with minimal greenhouse gases. The oceans might begin to evaporate, creating a runaway greenhouse effect. If this happens, complex life on Earth has already lived through most of its potential lifespan. We're not just at the Sun's midpoint, we might be near the end of Earth's habitable period, cosmically speaking. It's a sobering thought, though still comfortably distant in human timescales. Ancient sunlight, trapped in amber or ice, can tell us about the Sun's past behavior. Tiny bubbles of air preserved for millions of years contain isotopes created by solar radiation, giving us a window into ancient solar activity. The Sun's radiation doesn't just warm and illuminate, it also creates chemical changes in Earth's atmosphere. Cosmic rays and solar particles interact with nitrogen and oxygen, creating radioactive isotopes like carbon-14 and beryllium-10. The production rate of these isotopes depends on solar activity. During periods of high solar activity, the Sun's stronger magnetic field deflects more cosmic rays, reducing isotope production. During quiet periods, more cosmic rays reach Earth, and isotope production increases. These isotopes get incorporated into plants through photosynthesis and eventually into tree rings, ice cores, and even trapped air bubbles in amber or ancient ice. By measuring the concentrations of these isotopes, scientists can reconstruct solar activity going back thousands or even millions of years. Tree rings provide an annual record going back about 10,000 years. Ice cores from Antarctica and Greenland extend the record back hundreds of thousands of years. This research has revealed interesting patterns. The Sun's 11-year cycle appears in the isotope record, confirming it's been operating for at least thousands of years. There are also longer-term variations, periods of unusually high or low activity, lasting decades or centuries. The Maunder minimum, a period from about 1645 to 1715 when sunspot activity was extremely low, corresponds to the coldest part of the Little Ice Age in Europe. Ancient sunlight, frozen in time, tells us stories about our star. The Sun has not been perfectly constant. It has moods and variations that play out over decades and centuries. These variations are small compared to the sun's total output, but they might have subtle effects on Earth's climate. By studying the sun's past recorded in ice and wood and amber, we can better understand its present behavior and perhaps even predict its future fluctuations. The sun looked different 4 billion years ago when life first emerged on Earth. Dimmer and slightly cooler. Life had to adapt as the sun gradually brightened. A slow transformation spanning billions of years. 4 billion years ago, when the first self-replicating molecules were forming in Earth's oceans or hydrothermal vents or shallow pools, the sun was about 25% to 30% dimmer than today. Its surface temperature was slightly lower, perhaps 5300 degrees instead of today's 5500 degrees. It would have appeared slightly more orange than the yellow-white we see today. Early life evolved under this fainter star. The first photosynthetic organisms, probably something like modern cyanobacteria, developed systems to capture sunlight for energy. These systems evolved under specific light conditions, and they've had to adapt as the sun brightened. Photosynthesis became more efficient, or organisms evolved protective mechanisms against increasing radiation. The biosphere as a whole has had to adapt. As the sun brightened and Earth's surface temperature increased, the amount of greenhouse gases in the atmosphere decreased, partly through natural weathering processes, partly through biological activity. Plants and algae absorbed carbon dioxide. Shells and skeletons locked carbon into limestone. The atmosphere evolved from one dominated by CO2 to one dominated by nitrogen and oxygen, helping to regulate temperature even as the sun's output increased. This is coevolution on the grandest scale, life and star evolving together, not through direct interaction, but through the intermediary of Earth's climate and atmosphere. Life has been adapting to a changing sun for billions of years. The sun that shines on us today is not the sun that shone on the first life. And the sun that will shine 1 billion years from now will be different again. Life, if it still exists on Earth, will need to continue adapting or face extinction. The sun changes slowly, but it does change, and life must change with it. It's dangerous to look directly at the sun because it can permanently damage your retinas. The sun is so bright that even brief exposure can burn the sensitive cells in your eyes without you feeling pain until it's too late. Your eyes have evolved to see reflected light, sunlight bouncing off objects around you. They're not designed to look at the source of that light directly. The sun is so bright that focusing its light onto your retina concentrates enough energy to literally burn the tissue. The cells that detect light, rods and cones, are destroyed. And because the retina has no pain receptors, you don't feel it happening. The damage is often not immediately apparent. You might look at the sun during an eclipse or out of curiosity, look away feeling fine, and only hours later notice a dark spot in your vision. By then, the damage is done. The cells are dead and they don't regenerate. The blind spot is permanent. In severe cases, central vision can be lost entirely, leaving only peripheral vision. This is why solar eclipses are dangerous. During a partial eclipse, the sun is still bright enough to damage your eyes, but the novelty and reduced glare might tempt you to look longer. During totality, it's safe to look. The bright photosphere is completely blocked. But the moment totality ends and the diamond ring appears, you must look away immediately. that first flash of photosphere is still bright enough to cause damage. Special eclipse glasses or solar filters are necessary to view the sun safely. These reduce the sun's brightness by a factor of 100,000 or more, allowing you to look at it without damage. Regular sunglasses are not sufficient. They reduce brightness, but not nearly enough. The sun deserves respect. It gives us life, warmth, and light. But its radiance is so intense that we must shield our eyes from its direct gaze. We can study it, photograph it, worship it from afar, but we cannot look upon it directly without paying a price. Special telescopes allow scientists to observe the sun in different wavelengths, revealing features invisible to the human eye. In ultraviolet or X-ray light, the sun looks dramatically different, a seething, dynamic star rather than a steady yellow disk. Our eyes see only a narrow slice of the electromagnetic spectrum, wavelengths from about 400 to 700 nanometers, which we perceive as colors from violet through red. But the sun emits radiation across a much broader spectrum, from radio waves through gamma rays. Different wavelengths reveal different features. In visible light, we see the photosphere, the apparent surface. In hydrogen alpha wavelengths, 656 nanometers, a specific red wavelength, we see the chromosphere and prominences. In extreme ultraviolet and X-rays, we see the corona, the superheated outer atmosphere invisible in visible light. In radio wavelengths, we can detect solar storms and track the solar wind. Spacecraft like NASA's Solar Dynamics Observatory image the sun continuously in multiple wavelengths. In these images, the sun looks nothing like the calm yellow disk we see from Earth. It's a roiling, dynamic object covered in bright, active regions, dark coronal holes, loops and arcs of plasma following magnetic field lines. The corona is not smooth but structured, with bright spots and dark voids. Features appear and disappear on timescales of minutes to days. By observing in multiple wavelengths simultaneously, scientists can study different layers of the solar atmosphere and track how energy and matter move through them. A solar flare, for instance, appears as a bright flash in X-rays, a slower brightening in ultraviolet, disruption of the photosphere in visible light, and a blast of radio waves. Each wavelength tells part of the story. Together they reveal the sun as it truly is, not a simple, static sphere of light, but a complex, layered, dynamic star with weather and structure, extending from its core to millions of miles into space. The Solar Dynamics Observatory, SDO, has been photographing the sun every 0.75 seconds since 2010. This means we have over 1 billion high-resolution images of our star, creating an unprecedented record of its moods. Every 3/4 of a second in multiple wavelengths, capturing the sun's full disk at high resolution. For over a decade, without pause, the SDO has been watching. The data volume is staggering, about 1.5 terabytes per day, over 5 petabytes total since launch. This continuous monitoring has revolutionized solar physics. Before SDO, solar observations were more sporadic, snapshots rather than video. Now we have a complete record. We can watch solar flares develop in real time, see how prominences evolve over hours and days, track sunspots as they rotate across the disk. We can create time-lapse videos showing months or years of solar activity compressed into minutes. This data has led to discoveries. Scientists have observed phenomena that were previously too brief or too subtle to catch. Waves propagating through the solar atmosphere, magnetic field lines, reconnecting and releasing energy. Material raining down onto the surface along magnetic loops. The sheer volume of data allows for statistical studies that were impossible before. How often do flares of different sizes occur? How do sunspots affect local conditions? How does the corona respond to changes in the photosphere below? The STO's images are also publicly available. Anyone can view them, download them, create their own visualizations. Time-lapse videos of the sun have become popular online, mesmerizing sequences showing our star's continuous activity. The sun is never still, never boring. It's constantly changing. And for the first time in history, we have the tools to watch every change, to capture every mood, to build a comprehensive record of our star's behavior. Helioseismology is the study of waves moving through the sun, similar to how seismology studies earthquakes. By analyzing millions of oscillations on the sun's surface, scientists can probe its hidden interior. The sun rings like a bell, resonating with millions of different frequencies simultaneously. These oscillations are caused by sound waves, pressure waves, bouncing around inside the sun. They're created by the turbulent convection near the surface, and they propagate through the interior, reflecting off the core and the surface, creating standing wave patterns. These waves cause the solar surface to rise and fall by tiny amounts, typically a few centimeters to a few kilometers in height, with periods ranging from about 3 to 15 minutes. By measuring these oscillations precisely using Doppler shifts in spectral lines, scientists can determine which frequencies are present. Just as a bell's tone tells you about its size, shape, and material, the sun's oscillation frequencies reveal its internal structure. Different frequencies penetrate to different depths. High-frequency waves stay near the surface. Low-frequency waves dive deep into the interior before returning to the surface. By analyzing the complete spectrum of oscillations, scientists can map out how sound speed, which depends on temperature and composition, varies with depth inside the sun. This technique has allowed us to determine the sun's internal structure far more precisely than would be possible through theory alone. Helioseismology has confirmed that the sun's core is about 15 million degrees Celsius, that the transition from radiative to convective energy transport occurs at about 70% of the solar radius, and that the sun's rotation rate varies with depth and latitude in complex ways. It's revealed details about the sun's internal magnetic field and helped us understand how the solar dynamo operates. By listening to the sun's vibrations, we've learned to see inside our star, revealing secrets hidden beneath its bright surface. The sun rings like a bell with millions of different frequencies simultaneously. These vibrations create patterns that reveal the sun's internal structure, like using sound to see inside a drum. If you could hear the sun, if sound could travel through space, you'd hear a deep, complex drone composed of millions of overlapping tones. Most of these frequencies are far below human hearing, with periods of minutes rather than the fractions of a second our ears detect. But if you sped them up or shifted them into the audible range, the sun would sound like a vast chorus of tones all playing at once. These vibrations create visible patterns on the sun's surface. Different modes of oscillation create different patterns, some with the whole sun expanding and contracting, others with the northern and southern hemispheres oscillating out of phase, still others with complex patterns of nodes and antinodes across the surface, High-resolution images can show these patterns directly as regions of the surface moving up or down. The study of these patterns has revealed details that would otherwise be hidden. For instance, sound waves travel faster through hotter material and slower through cooler material. By mapping how quickly waves travel through different parts of the sun, scientists can create temperature maps of the interior. They've discovered that the base of the convective zone is not perfectly spherical. It has bumps and depressions driven by convection patterns. They've measured how fast different layers rotate, finding that the rotation rate varies smoothly with radius in the radiative zone, but has sharp transitions at the boundaries between different zones. The sun is transparent to these acoustic waves in a way it's not transparent to light. Sound can travel through the entire star, carrying information from the deep interior to the surface where we can detect it. By analyzing the sun's music, its vibrations and oscillations, we've learned to see through the glare and into the heart of our star. The Parker Solar Probe, launched in 2018, will eventually fly through the sun's corona at distances closer than any previous spacecraft. It will endure temperatures of 2,500 degrees while traveling at 430,000 mph, the fastest human-made object ever built. The Parker Solar Probe is humanity's most ambitious attempt to touch the sun. Over the course of its 7-year mission, it will make repeated passes through the sun's outer atmosphere, coming as close as 3.8 million miles from the surface, about 7 solar radii from the center. 3.8 million miles might sound distant, but in the context of the solar system, it's remarkably close. That's closer than Mercury ever gets. The spacecraft will be bathed in solar radiation 475 times more intense than what we experience at Earth. Without protection, it would vaporize in seconds. Even electronics that can withstand typical space conditions would fail almost immediately at those temperatures and radiation levels. And yet, the spacecraft isn't as hot as you might expect. While the corona around it reaches temperatures of over 1 million degrees Celsius, the spacecraft itself will only heat to about 1,400 degrees, 2,500 degrees, on its heat shield. This is because temperature and heat are different things. The corona is extremely hot. Particles are moving very fast. But it's also extremely tenuous. There are so few particles that even though each one has high energy, they can't transfer much heat to the spacecraft. It's like the difference between sticking your hand in a 400-degree oven, uncomfortable but briefly tolerable, versus touching a 400-degree metal pan, instant burn. At its closest approach, traveling at perihelion, the Parker Solar Probe reaches speeds of about 430,000 miles per hour, over 190 kilometers per second. At that speed, you could travel from New York to Tokyo in less than a minute. It's fast enough that time dilation becomes measurable, though tiny, about 100 microseconds per orbit. The probe is experiencing the sun's environment directly, measuring the solar wind at its source, flying through the coronal plasma, studying the mechanisms that heat the corona and accelerate the solar wind. It's sending back data that will help solve mysteries that have puzzled us for decades. To protect itself from the sun's heat, the Parker Solar Probe uses a carbon composite shield just 4.5 inches thick. Behind this shield, the spacecraft's instruments remain at comfortable room temperature while facing the sun's fury. The heat shield, officially called the Thermal Protection System, or TPS, is an engineering marvel. It's made of carbon-carbon composite, a material that can withstand temperatures up to 3,000 degrees Celsius without degrading. It's only 4.5 inches, 11.4 centimeters thick, but that's enough. The shield faces the sun constantly, maintained in position by precise attitude control. The sun-facing side heats to about 1400 degrees Celsius, glowing red hot. But the material is such a good insulator that the backside, just inches away, remains near room temperature, around 30 degrees, 86 degrees. The spacecraft's instruments and electronics sit in the shadow of this shield, protected from the inferno just beyond. This protection has to be active and continuous. If the spacecraft were to tumble and expose its instruments directly to the sun, they would be destroyed in seconds. The mission control team monitors the spacecraft's orientation carefully, and the spacecraft has autonomous systems to correct any anomalies. The heat shield must always face the sun, like a sunflower following the sun across the sky, except this sunflower is traveling at 430,000 miles per hour while maintaining its orientation to within a fraction of a degree. It's a testament to human ingenuity that we can build something that survives these conditions. We're sending instruments into the sun's atmosphere, a place where no solid material should exist, and bringing back data. The heat shield is the key, a thin layer of carbon standing between room temperature and 1400-degree plasma, allowing us to study our star up close for the first time. Behind that shield, civilization's most sophisticated instruments sit comfortable and cool, watching the sun's corona swirl around them, measuring phenomena that have been invisible or inaccessible until now. Ancient astronomers tracked sunspots with the naked eye, using safely dimmed light during sunrise or sunset. Chinese records of sunspots date back over 2,000 years, making them one of the oldest continuous scientific observations. In ancient China, astronomers serving the imperial court kept meticulous records of celestial phenomena. They recorded comets, eclipses, meteor showers, and sunspots. These records, preserved in historical texts, provide a window into the sun's behavior going back more than 2 millennia. The oldest definite sunspot record is from 28 BCE, though there may be older, more ambiguous references. Chinese astronomers described sunspots as dark blemishes or marks on the sun, sometimes comparing them to coins or flying birds. They observed them during sunrise or sunset when the sun's light was dimmed by atmospheric haze, or through thin clouds that acted as natural filters. These observations were sporadic. Sunspots are not always visible to the naked eye, and they require relatively clear atmospheric conditions and sufficiently large spot groups. But over centuries, enough observations accumulated to show that sunspots appeared in cycles, that they moved across the sun's face, evidence of solar rotation, and that they varied in number and size over time. Western astronomers didn't systematically observe sunspots until Galileo's telescopic observations in the early 1600s, but the Chinese records show that humans have been aware of sunspots for far longer. These ancient observations are not just historical curiosities, they're valuable scientific data. By combining ancient Chinese, Korean, and Japanese sunspot records with modern observations, scientists have reconstructed solar activity going back over 2,000 years, revealing long-term patterns and variations that wouldn't be visible in the shorter modern record alone. Different cultures have worshipped the sun as a deity. Ra in Egypt, Amaterasu in Japan, Inti in the Inca Empire. This universal reverence reflects humanity's deep understanding that the sun is the giver and sustainer of life. Throughout human history, across continents and cultures, people have looked up at the sun and recognized it as something worthy of reverence. In ancient Egypt, Ra was the sun god and one of the most important deities, often depicted with a falcon head crowned with a solar disk. Pharaohs claimed descent from Ra, linking their divine right to rule with the power of the sun. In Japan, Amaterasu is the sun goddess and the mythical ancestor of the Japanese imperial line. Her name means shining in heaven, and she represents the sun's life-giving light. In Shinto belief, when she hid in a cave, angered by her brother's destructive behavior, darkness fell upon the world until the other gods lured her out, restoring light to the world. The Inca Empire in South America worshipped Inti, the sun god, as the divine ancestor of their rulers. The most important Inca festival, Inti Raymi, celebrated the winter solstice and the sun's return. Even today, a modern version of this festival is celebrated in Peru. These aren't isolated examples. The Aztecs worshipped Tonatiuh, believing that human sacrifice was necessary to keep the sun moving across the sky. The Norse had Sol, a goddess who drove the sun chariot across the heavens. Hinduism has Surya, the solar deity. Many Native American tribes have sun deities or spirits. The list goes on. This near-universal sun worship isn't superstition or ignorance. It's a profound recognition of reality. The sun is the giver of life, the source of warmth, the marker of time, the driver of seasons. Without it, there is only darkness, cold, and death. Our ancestors understood this intuitively. They may not have known about nuclear fusion or the solar wind, but they knew that the sun was essential, powerful, and worthy of respect and gratitude. In recognizing the sun's importance, they were absolutely correct. The amount of solar energy hitting Earth in 1 hour could power human civilization for an entire year. We're living on a planet bathed in more energy than we could ever use, if only we could capture it efficiently. Every hour, about 430 quintillion joules of solar energy reach Earth's surface and atmosphere. Global human energy consumption is about 580 exajoules per year. That means 1 hour of sunlight provides enough energy for humanity's needs for an entire year, with energy to spare. Of course, capturing all that energy is impractical. Much of it falls on oceans, where collection is difficult. Much falls in remote locations, far from where energy is needed. Weather, day-night cycles, and seasons mean that solar energy is intermittent. Storage technology would be needed to save energy from sunny times for use during cloudy times or at night. But even capturing a small fraction would be transformative. The total land area suitable for solar panels, deserts, rooftops, marginal land, could theoretically generate far more electricity than humanity currently uses. If we covered less than 2% of Earth's land area with even moderately efficient solar panels, we could meet all of humanity's current energy needs. Solar technology is improving and becoming cheaper. In many locations, solar power is now the cheapest form of new electricity generation. As technology improves and costs continue to fall, solar energy is gradually shifting from a niche source to a major component of the global energy system. We're learning, slowly, to accept the gift the sun has been offering all along. Abundant, clean energy delivered free every day. The challenge isn't the amount of energy available. The sun provides abundance. The challenge is learning to capture, store, and distribute it efficiently. We're working on it, gradually developing the technology to live off the sun's current income rather than Earth's ancient solar savings stored in fossil fuels. Scientists don't fully understand how the sun generates its precise 11-year activity cycle. Despite decades of study, the sun's magnetic heartbeat remains one of its most intriguing mysteries. We know the cycle exists. It's been reliably observed for over 150 years, and historical records suggest it's been operating for at least thousands of years. We know it's related to the sun's magnetic field, which builds up, becomes complex and tangled, flips polarity, and rebuilds again. We know it's connected to the solar dynamo, the process by which convection and differential rotation generate and amplify magnetic fields. But we don't fully understand why the cycle is 11 years long. Why not 5 years or 20 years? What determines the timing? We have models that reproduce the general behavior. Magnetic fields generated in the convective zone, amplified by differential rotation, rising to the surface as sunspots, eventually reversing polarity. But these models don't perfectly predict the cycle's details. Moreover, the cycle is variable. Some solar cycles are strong with many sunspots. Others are weak with few spots. The most recent solar minimum, from about 2008 to 2010, was unusually deep and prolonged, with very few sunspots for an extended period. No one fully predicted this or can completely explain why it happened. The sun, it seems, has moods and variations that our models don't capture. There's also the question of longer-term patterns. Are there cycles longer than 22 years, the full magnetic cycle? Does the sun have grand minima, long periods of reduced activity like the Maunder minimum in the 1600s? And if so, what causes them? How does the sun's magnetic field interact with its rotation, convection, and other internal dynamics to produce these patterns? The sun's magnetic cycle is regular enough to predict broadly, but complex enough to surprise us. It's a reminder that even our closest star, the one we've studied most intensively, still guards secrets. We're getting closer to understanding, but complete comprehension remains just out of reach. The sun's magnetic field is incredibly complex, constantly tangling, snapping, and reconnecting. This invisible architecture shapes everything we see on the solar surface: spots, flares, prominences, and storms. If you could somehow visualize the sun's magnetic field, you'd see it's far from simple. It's not a clean dipole like Earth's magnetic field, with a clear north and south pole and field lines arcing smoothly from pole to pole. Instead, the sun's field is a chaotic tangle of loops, arcs, and bundles of field lines threading through the photosphere and extending into the corona. These field lines are frozen into the plasma. Where the plasma moves, it drags the magnetic field with it. And the plasma is constantly moving, convection cells rising and falling, differential rotation shearing the field, turbulence creating eddies and knots. The field becomes twisted, stretched, compressed, and tangled. Like rubber bands being wound tighter and tighter, magnetic energy builds up. Eventually, the stress becomes too great. Field lines snap and reconnect in a new configuration, releasing the stored magnetic energy explosively. This is magnetic reconnection, and it's the mechanism behind solar flares and coronal mass ejections. The energy released can heat plasma to tens of millions of degrees, accelerate particles to near light speed, and hurl billions of tons of material into space. Sunspots are places where strong magnetic field lines emerge from below the surface, forming loops that extend through the corona before diving back down at another sunspot of opposite polarity. Prominences are plasma trapped in magnetic loops suspended above the surface. Coronal holes are regions where field lines don't loop back but extend out into space, creating pathways for fast solar wind. Everything dynamic on the Sun, everything except the basic fusion in the core, is driven by magnetic fields. The Sun's visible face is a map of its invisible magnetic architecture. Every structure, every event, traces back to the tangled, ever-changing magnetic field that permeates the Sun and shapes its behavior. Some researchers believe the Sun may have had a binary companion star early in its history that was lost or ejected. If true, the Sun once had a sibling that departed billions of years ago, leaving us alone with our parent star. Most stars form in groups or pairs. Binary and multiple star systems are extremely common, perhaps more common than single stars like the Sun. When a molecular cloud collapses to form stars, it often fragments, creating multiple stars that orbit each other. Given that star formation typically produces binaries, why is the Sun alone? There are several possibilities. The Sun might have always been single, a relatively rare but not impossible outcome of stellar formation. Or it might have formed with a companion that was later lost. Simulations show that young star clusters are dynamic, chaotic places where gravitational interactions between stars can eject low-mass companions from their orbits. If the Sun had a low-mass companion, it might have been stolen by a passing star or ejected through three-body interactions in the birth cluster. Some astronomers have speculated about a hypothetical distant companion, sometimes called nemesis or Tyche, to explain patterns in the solar system or in mass extinctions on Earth. However, searches have found no evidence for such a companion. If it exists, it would have to be very far away and very faint, perhaps a brown dwarf or a dim red dwarf many thousands of AU from the Sun. The truth is, we don't know. The Sun's early history is lost to time. Its birth cluster has long since dispersed, its members scattered across the galaxy. If the Sun once had a sibling star, it's now lost among the billions of other stars. Its connection to our Sun unknowable. We orbit alone around a single star, but this might be a historical accident rather than the original configuration. Perhaps somewhere out there, thousands of light years away, there's a star that formed in the same nebula as the Sun, a distant cousin we'll never identify. The concept of solar weather didn't exist until the space age. We only recently discovered the Sun is so variable. For most of human history, the Sun was thought to be eternal and unchanging, a perfect celestial object, before the space age, before satellites and continuous monitoring, before we could observe the Sun in ultraviolet and X-rays. It seemed stable. It rose each morning, crossed the sky, and set each evening with perfect regularity. Its brightness seemed constant. Its appearance, a smooth, featureless disk to the naked eye, seemed unchanging, eternal. This was the prevailing view through most of history. The Sun was perfect, divine, immutable. When Galileo observed sunspots in 1612, it was revolutionary because it showed the Sun had imperfections, that it changed. But even then, the changes seemed minor, dark spots appearing and disappearing, evidence of rotation but not of violent activity. It wasn't until the space age that we discovered how dynamic the Sun really is. Satellites equipped with X-ray and ultraviolet detectors revealed that the sun has weather. Solar flares erupting without warning, coronal mass ejections hurling plasma into space, the solar wind varying in speed and density, the corona flickering with reconnection events. The sun we see from space is not the calm, steady yellow disk visible to the naked eye. It's a roiling, active, sometimes violent star. The concept of space weather, the idea that conditions in near-Earth space can change dramatically due to solar activity, affecting satellites, power grids, and communications, didn't exist until the 1970s and 1980s. Now it's an entire field of study with operational forecasting, much like terrestrial weather prediction. We monitor the sun continuously, watch for flares and CMEs, predict when they might reach Earth, and issue warnings to power companies and satellite operators. We've come to understand that the sun, far from being perfect and unchanging, has moods and storms just like Earth's atmosphere. It has quiet periods and active periods, calm days and violent outbursts. The sun is alive with activity, and we're only now, in the last few decades, learning to observe and understand the solar weather that our ancestors never knew existed. Neutrons produced by solar flares can reach Earth and be detected by specialized instruments. These ghostly particles are created in nuclear reactions on the sun and travel 93 million miles to Earth in about an hour. During a powerful solar flare, the temperatures and energies involved can trigger nuclear reactions in the solar atmosphere. Protons, hydrogen nuclei, are accelerated to nearly the speed of light and collide with other atoms in the chromosphere and photosphere. These collisions can knock neutrons out of atomic nuclei, creating free neutrons. Neutrons are unstable outside of atomic nuclei. They decay with a half-life of about 10 minutes, turning into protons, electrons, and antineutrinos. But 10 minutes is enough time for some of them to make the journey from Sun to Earth. Traveling near the speed of light, neutrons can reach Earth in about an hour after being produced. By the time they arrive, many have decayed, but enough survive to be detected. Special instruments called neutron monitors, stationed at high altitudes and at various locations around the world, detect these solar neutrons along with cosmic ray neutrons from other sources. When a major solar flare occurs on the Earth-facing side of the sun, neutron monitors see a spike in counts. This is called a ground level enhancement, or GLE, event. These solar neutrons are messengers carrying information about the nuclear processes happening during flares. They tell us about the energies and temperatures involved, about how particles are accelerated, about the structure of the magnetic fields channeling those particles. They're also a potential radiation hazard for astronauts and high-altitude aircraft passengers during major solar storms. It's remarkable that we can detect individual particles created in nuclear reactions on the sun's surface. These neutrons began their existence in a solar flare, a violent magnetic reconnection event millions of miles away, and ended their journey striking a detector on Earth. They're a tangible connection between the sun's violence and our world, messengers from a star. The sun produces neutrinos constantly. Trillions pass through your body every second without interacting. These nearly massless particles escape the sun's core immediately, carrying information about fusion reactions happening right now. Neutrinos are ghostly particles, barely interacting with matter at all. They have almost no mass, no electric charge, and they're produced copiously in the nuclear reactions happening in the sun's core. Every time 4 hydrogen nuclei fuse to form one helium nucleus, 2 neutrinos are released and escape immediately. Unlike photons, which take tens of thousands of years to random walk through the sun's dense interior, neutrinos simply fly straight out. They don't care about the plasma, the density, the atoms in their way. They pass through matter as if it weren't there. In the time it takes you to read this sentence, trillions of neutrinos from the sun have passed through your body, through your eyes, your brain, your heart, without leaving a trace, without interacting with a single atom. This makes neutrinos both fascinating and frustrating. Fascinating because they carry information directly from the core, telling us about fusion reactions happening right now rather than tens of thousands of years ago. Frustrating because they're nearly impossible to detect. Most neutrinos pass through the entire Earth as easily as they pass through your body. To detect them, you need enormous detectors, swimming pools full of ultra-pure water or cleaning fluid, buried deep underground to shield them from cosmic rays. And even then, you might detect only a handful of solar neutrinos per day. The neutrinos streaming through you right now were created seconds ago in the sun's core. They're fresh news from the solar furnace, proof that fusion is happening this very moment. If fusion suddenly stopped in the sun's core, we wouldn't see any difference in sunlight for tens of thousands of years. But we'd know within 8 minutes because the neutrinos would stop arriving. They're our real-time connection to the sun's heart, invisible messengers, passing through us constantly, mostly unnoticed, but profoundly significant. Detecting solar neutrinos was so difficult that it took decades and massive underground detectors to confirm they existed. The solar neutrino problem puzzled physicists for 30 years, until we realized neutrinos could change types mid-flight. In the 1960s, physicist Raymond Davis Jr. built a detector deep in a gold mine in South Dakota to catch solar neutrinos. The detector was a tank containing 100,000 gallons of cleaning fluid. Very occasionally, perhaps once a day or every few days, a neutrino would interact with a chlorine atom in the fluid, converting it to argon. Davis would periodically extract the argon atoms and count them. The experiment worked. Neutrinos were detected. But there was a problem. The number was wrong. Davis was detecting only about 1/3 the number of neutrinos predicted by models of the sun's core. This was a solar neutrino problem. Either our understanding of the sun was wrong, maybe fusion wasn't happening as we thought, or something was wrong with our understanding of neutrinos. For 3 decades, this puzzle persisted. Other experiments confirmed the deficit. The sun seemed to be producing fewer neutrinos than expected, or neutrinos were disappearing somehow between the sun and Earth. Then, in the 1990s and early 2000s, experiments in Japan, Canada, and elsewhere made a remarkable discovery. Neutrinos can change flavor. There are 3 types of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces electron neutrinos through fusion, but during their journey to Earth, some of these electron neutrinos oscillate into muon or tau neutrinos. Davis's detector was only sensitive to electron neutrinos, so it missed the ones that had changed when experiments that could detect all 3 flavors were built. They found the total number of neutrinos matched predictions perfectly. This solved the solar neutrino problem and revealed something profound about neutrinos. They have mass. Massless particles can't oscillate between types. The discovery that neutrinos oscillate and therefore have mass was groundbreaking, earning the Nobel Prize in Physics in 2015. A problem with the sun led to a fundamental discovery about particle physics. If the sun's fusion suddenly stopped, we wouldn't notice any change in sunlight for about 170,000 years. The energy would continue its slow journey outward, keeping the sun shining long after its heart had gone dark. This is one of the strangest facts about the sun. The light warming your skin right now was created in the sun's core, tens of thousands of years ago, possibly longer. It's been bouncing around inside the sun all that time, slowly working its way outward through countless absorption and re-emission events in the radiative zone. If fusion suddenly stopped, if some cosmic switch turned off the nuclear reactions in the core, nothing would immediately change. The core would stop producing new gamma rays, but the photons already in the radiative zone would continue their random walk outward. The sun would continue shining from stored energy, like a kettle remaining hot for a while after you turn off the stove. How long would this last? Estimates vary, but somewhere between 10,000 and 200,000 years, with 170,000 years being a reasonable middle estimate. During this time, the sun would gradually dim as the stored energy depleted and wasn't replenished by new fusion. But the change would be so slow, perhaps a fraction of a percent per century, that it would be difficult to notice within a human lifetime. Eventually, of course, the energy would run out. The sun's outer layers, no longer supported by outward radiation pressure, would begin to contract under gravity. The contraction would heat the core, possibly reigniting fusion, or the sun might continue contracting into some other configuration. But for many millennia, the sun would shine on, a ghost powered by ancient light. Its heart dark, but its face still bright. It's a peculiar thought, that the sun could die on the inside while continuing to appear alive on the outside for longer than human civilization has existed. The light we see is always old, always carrying news from the sun's past. We're forever looking backward in time when we look at the sun, seeing not what it is, but what it was. The sun's gravity affects space-time itself, creating what Einstein called a gravitational well. Planets don't orbit because of an invisible force pulling them. They roll along curves in warped space created by the sun's mass. Newton described gravity as a force, an invisible attraction between masses. In his model, the sun pulls on Earth, and Earth pulls on the sun, and this force keeps Earth in orbit. It was a useful model, accurate for most purposes, and it served us well for centuries. But Einstein showed that gravity isn't really a force. It's a consequence of curved space-time. Mass warps the fabric of space and time around it, creating curves and dips in space-time geometry. What we experience as gravity is simply objects following the straightest possible paths, geodesics, through this curved space-time. The sun, being massive, creates a deep gravitational well in space-time. If you could visualize it in 2 dimensions, it would look like a bowling ball placed on a stretched rubber sheet, creating a depression. Earth isn't being pulled toward the sun by a force. It's rolling along the curved surface created by the sun's mass. Earth's orbital motion is its attempt to travel in a straight line through curved space-time, and that straight line happens to be a closed ellipse around the sun. This isn't just philosophy or interpretation, it's measurably true. Light passing near the sun bends because it's following curved space-time. This was confirmed during a solar eclipse in 1919, when stars appeared slightly shifted from their true positions because their light curved around the sun. Time also runs differently in a gravitational well. Clocks on the sun's surface tick slightly slower than clocks on Earth, and GPS satellites have to account for time dilation to maintain accuracy. The sun doesn't just illuminate space, it shapes it. The geometry of the solar system is defined by the sun's mass warping space-time. We live in curved space, following curved paths, experiencing time that flows at different rates depending on where we are in the sun's gravitational well. There are places in the solar system where the sun appears only as a very bright star rather than a disk. Beyond the orbit of Neptune, the sun looks nothing like we see it from Earth, just an intense point of light in the darkness. Imagine standing on Neptune's moon Triton, or on Pluto, or on one of the distant objects in the Kuiper Belt, 30 to 50 times farther from the sun than Earth is. The sun would still be the brightest object in the sky by far, brighter than any other star. But it wouldn't be the large, warm disk we see from Earth. It would appear as a point of light, perhaps showing a tiny disk if you looked through binoculars. But to the naked eye, it would look like a star. At that distance, the sun provides very little warmth. On Pluto, surface temperatures hover around 230 degrees, 380 degrees, cold enough to freeze nitrogen and methane into solid ice. The sunlight reaching Pluto is about 1,600 times weaker than sunlight reaching Earth. Intense enough to read by perhaps, but not warm enough to melt ice or drive weather systems. Even further out in the Oort cloud at distances of tens of thousands of AU, the sun would be just another bright star among many. It would still be visible, still identifiable as the sun if you knew where to look, but it would have lost all appearance of being special. You'd be in true interstellar space, where the sun's light is barely distinguishable from other nearby stars, where darkness and cold dominate. The sun's influence extends far beyond where it appears as a disk. Its gravity holds the Oort cloud in orbit. Its light, however faint, still provides some illumination. Its solar wind, though thin and weak, still reaches those distances. But to an observer in the outer solar system, the sun is no longer the overwhelming presence it is from Earth. It's a distant point of light, a reminder that even stars have a limited reach. That distance diminishes everything, even the sun. The sun contains enough hydrogen to continue fusing for another 5 billion years at its current rate. This gives life on Earth, or whatever succeeds us, eons to develop, spread, and perhaps find a new home before the end. 5 billion years is an almost incomprehensible span of time. The Earth itself is only 4.5 billion years old. 5 billion years ago, the sun was just forming, and Earth didn't yet exist. 5 billion years from now is equally distant into the future. It's longer than complex life has existed on Earth, longer than the continents have had recognizable shapes. In 5 billion years, continents will have drifted into completely different configurations. New mountain ranges will have risen and eroded away. Species will have evolved, radiated, gone extinct, and been replaced by others countless times. If humanity, or whatever our descendants become, survives even a fraction of that time, we'll have had billions of years to develop, explore, and perhaps spread to other star systems. 5 billion years is enough time to develop technologies we can barely imagine, to solve problems that currently seem insurmountable, to become something entirely different from what we are now. It's enough time for intelligence to spread throughout the galaxy, to build civilizations among the stars, to find other life or create it, to transform worlds and perhaps even stars themselves. And yet, it's finite. The sun will run out of fuel. Earth's time as a habitable world is even more limited, perhaps only another billion years before the sun's gradual brightening makes Earth too hot for complex life. But that's still a billion years, still vast stretches of time for evolution, development, and change. The sun has given us time, an enormous gift of temporal space to grow, learn, and become whatever we're capable of becoming. The deadline is distant but real. What we do with that time is up to us. Every sunset and sunrise you see is light that began its journey in the sun's core when your great-great-great-great-grandparents' ancestors hadn't been born yet. The light took so long to escape that it's older than human civilization, finally freed to race across space. When you watch a sunset, the light entering your eyes began as gamma rays, produced by fusion in the sun's core, perhaps 100,000 years ago. Those photons spent millennia bouncing randomly through the radiative zone, absorbed and re-emitted countless times, gradually losing energy and shifting toward longer wavelengths. 100,000 years ago, humans existed, but were not yet anatomically modern. We hadn't developed complex language, art, or symbolic thought. We were still early in our evolution as a species, and photons that would eventually become the sunset you watch were just beginning their long journey through the sun's interior. They traveled through the radiative zone, through the convective zone, finally emerging from the photosphere. Then they crossed 93 million miles of empty space in just over 8 minutes, finally arriving at Earth, passing through the atmosphere and entering your eye. Their journey from creation to your retina took 100,000 years, give or take. They're older than agriculture, older than cities, older than writing. They're ancient light, finally freed after an imprisonment lasting longer than recorded history. Every moment of sunlight you experience is a connection to the deep past, not the sun's recent past 8 minutes ago, but it's past from the era when humans were just beginning to become human. The photon striking your eye right now is older than any human civilization. It's a time traveler, carrying a message from an era before history, before language, before we had words to describe what light even was. And you're receiving that message now, 100,000 years after it began its journey, completing a story that started before your ancestors knew how to tell stories. The sun is the only star we can study in detail, making it our laboratory for understanding all other stars. Everything we know about distant stars comes partly from our intimate knowledge of the one we orbit. We can observe other stars, certainly. We can measure their brightness, analyze their spectra, track their motion, even detect their planets. But we can't see their surfaces in detail. We can't watch their sunspots rotate across their disks. We can't resolve their granulation patterns or observe individual prominences. They're too distant, appearing only as points of light even through our largest telescopes. The sun is different. It's close enough to study in exquisite detail. We can observe its surface features, measure its oscillations, track plasma flows, watch flares develop in real time, map its magnetic field. We can send spacecraft to sample its atmosphere directly. The Sun is our stellar physics laboratory, the one star where we can test theories and observe phenomena up close. Everything we've learned about stellar structure, stellar atmospheres, stellar magnetic fields, stellar oscillations, and stellar evolution has been informed by observations of the Sun. When we model other stars, we use physics developed and tested by studying the Sun. When we observe phenomena on other stars, star spots on distant stars, flares on red dwarfs, oscillations in other Sun-like stars, we interpret them in light of what we've learned from our Sun. This makes the Sun uniquely valuable. It's not just important because it's our star, because it provides light and warmth to our planet. It's important because it's the Rosetta Stone of stellar physics, the key that unlocks our understanding of all the other stars we see in the night sky. By studying the one star we can see clearly, we learn to read the stories written in the light of stars we can never visit, scattered across vast distances throughout the galaxy and beyond. No human technology can recreate the conditions in the Sun's core. Our fusion experiments require different approaches. The Sun uses gravity and time to achieve what we try to accomplish with magnetic fields and lasers. The Sun makes fusion look easy. It's been doing it for 4.6 billion years without fail, converting hydrogen to helium at a steady, reliable rate. But the conditions that make this possible, 15 million degrees Celsius, pressures 250 billion times Earth's atmospheric pressure, maintained throughout a volume larger than Earth, are far beyond our ability to reproduce. We've achieved fusion on Earth, but we do it differently. In thermonuclear weapons, we use fission explosions to create the necessary temperatures and pressures for a fraction of a second, just long enough for fusion to occur before the weapon explodes. In experimental fusion reactors, we use powerful magnetic fields to confine plasma at temperatures of 100 million degrees or more, hotter than the Sun's core, because our plasma is less dense and we need higher temperatures to achieve the same fusion rate. We use lasers to compress tiny pellets of fuel, creating conditions where fusion can occur for nanoseconds. We explore alternatives like muon-catalyzed fusion or anetronic fusion reactions. But none of these approaches can match the Sun's elegant solution. Use gravity to squeeze a massive amount of hydrogen, wait for it to heat up from gravitational compression, and let fusion occur steadily for billions of years. The Sun's approach requires stellar masses of material and billions of years, resources we don't have and patience we can't afford. So we search for shortcuts, different paths to the same goal. We're trying to bottle starlight, to capture in magnetic fields what the Sun accomplishes with gravity. It's a testament to human ambition that we're even trying, that we've gotten as close as we have. But it's also a reminder of the Sun's power and elegance. What comes naturally to a star requires humanity's most sophisticated technology and still remains just out of reach. In all of human history, the Sun has been the most constant presence in our sky, rising, setting, and rising again for every generation that has ever lived. It was there before we were, and in some form, it will remain long after we're gone. A patient, distant companion to Earth's brief experiment with life. Think about this. Every human who has ever lived has known the Sun. Our ancestors, hundreds of thousands of years ago, woke to the same Sun that you see today. They felt its warmth on their skin, watched it move across the sky, used it to mark time and seasons. The ancient Egyptians building pyramids worked under this sun. The first humans painting on cave walls by firelight waited for this sun to rise. Every civilization, every empire, every person who has ever existed has shared the experience of sunlight. The sun has been our constant companion through all of human history and prehistory. It witnessed the evolution of our species, the development of language and art, the rise of agriculture and cities, the spread of humanity across the globe. It was there for every triumph and every tragedy, every birth and every death, shining impartially on all. And it will continue long after us. Even if humanity disappears tomorrow, the sun will keep shining. It will illuminate an earth without us, its light falling on forests and oceans that no human eye will see. It will continue for billions of years, eventually swelling into a red giant, engulfing the inner planets, shedding its outer layers, becoming a white dwarf that cools slowly in the darkness. The sun is both intimate and distant, familiar and alien. It's close enough that we feel its warmth, distant enough that we can never touch it. It's the giver of life and light, the reason we exist, and yet it's utterly indifferent to us. It shines for no purpose, follows no plan, cares nothing for the life it enables. It's simply a star doing what stars do, converting mass to energy through fusion, shining by the laws of physics. And yet, perhaps that's what makes it beautiful. The sun doesn't exist for us, but we exist because of it. We're the universe's way of seeing itself, matter that became aware and looked back at the star that made it possible. The sun has been here all along, patient and steady, waiting billions of years for something to evolve that could appreciate it, understand it, wonder at it. Every sunrise is a gift we didn't earn and don't deserve, yet receive anyway. Every sunset is a reminder that we're temporary, but the sun endures. We're brief sparks of consciousness, here for a moment against the backdrop of deep time, warmed by a star that will outlive us by billions of years. And in that brief moment, we've learned to understand our star, to measure it and study it, to appreciate its role in our story. Perhaps that's enough, to be here now, aware and wondering, grateful for the light. And so we've journeyed through 100 facts about the sun, from its nuclear heart to its vast atmosphere, from its formation billions of years ago to its death billions of years hence, from ancient observations to modern spacecraft flying through its corona. We've learned that the sun is both ordinary and extraordinary, average and essential, distant and intimate. The sun is just one star among hundreds of billions in our galaxy, trillions in the universe, and yet it's our star, the only one close enough to warm a world and allow life to flourish. It's the reason there's light to see by, air to breathe, food to eat. Everything we are traces back to this star in some way. We are children of the sun, made of stardust from ancient stars that died before the sun was born, living on sunlight stored in plants and fossil fuels, warmed by light that traveled for thousands of years inside the sun before reaching us. If you're still awake, listening to these words, perhaps look outside tomorrow and watch the sunrise. See it not just as a beautiful scene, but as a reminder of your connection to the cosmos. That light traveled 93 million miles to reach you. It's made of photons that spent thousands of years escaping from the sun's interior. It's the product of fusion reactions, converting mass to energy in the sun's core. It's ancient, powerful, and given freely. Or perhaps you've already drifted off, these final thoughts, accompanying you into sleep. That's fine too. The sun will rise tomorrow, whether you see it or not. It's been doing so for billions of years. It's patient. It will wait. Thank you for joining me on this journey through the science of the sun. May your sleep be peaceful, your dreams filled with starlight, and your waking hours touched by wonder at the vast, indifferent, beautiful universe we're lucky enough to inhabit. Good night.